This year, GYSS celebrates its 10th anniversary of the annual meeting between young scientists and engineers from all over the world, and outstanding scientists and engineers who got Nobel Prize, field medals, Millennium Technology Prizes, and Turing Awards. Last year, besides the problem of COVID-19 pandemic, I had a severe accident, and so I could not join the event even online. This year I can be with you online, and I am allowed to send more Thai young scientists to the event than the previous years. Besides having the opportunity to learn from global scientists and engineers from other young scientists and the visits to research institute in Singapore, these young people who are mostly in science and technology careers can be inspired to create the works that benefit Thailand and the world. As they become successful professionals in science and technology, they will inspire other children to pursue the same careers, and the government could see the importance of promoting more citizens to study science and technology. I hope that young scientists and researchers in science and technology won't be discouraged by the obstacles they encounter and continue to do their best. I hope that they will always think of new things as GYSS moves on to the next 10 years.
It's 10 years of Global Young Scientists Summit, and it's my pleasure to congratulate Singapore's National Research Foundation and also the organizers for having GIS this year, and I wish you a wonderful meeting. I'm very glad when I'm thinking of all the participants, being the current or the former ones, because having exchange about science is one of the best things you can do. We in Lindau also had an anniversary last year, and of course it's always great to have this recognition for the past, but at the same time it gives much motivation and energy to carry on, particularly in times like these. Thinking of the young people, my message for you, young scientists taking up a career in science and technology would be: do what you're really passionate about, be always curious and ready to share your knowledge, and a platform like the Global Young Scientists Summit is great for doing that. Sometimes I'm asked if I could get advice. I'm not within science, but my advice for further careers, of course with reference to a Nobel Prize, would be: despite all very obvious value in applied sciences, let's take COVID-19, do not lose sight of basic research, also for the sake of future generations. And now I hope you enjoy the GIS 22 and wish you all the best for it. Many greetings from Lindau.
The success of the Global Young Scientists Summit is a testament to the importance of borderless collaboration in the pursuit of excellence and the benefit of humanity. As we seek to tackle global challenges such as climate change, biodiversity loss, and protecting human health, and to pursue the knowledge of ourselves and the universe around us, this is the bedrock of future research, and it's your generation that will be at the forefront. The scale of these challenges may have inspired you all. I'm sure the desire to expand our understanding and make the world a better place will continue to inspire your generation. While the challenges are great, Your generation, like those before you, stand on the shoulders of giants. You have access to new knowledge and tools that can help change the world for the better. I urge you all to grasp the opportunities and pursue your passions.
The Global Young Scientist Summit, GYSS, was established 10 years ago in order to excite, engage, and inspire young researchers to pursue their passion, develop solutions in order to solve problems in our economy and in society. This has never been more necessary. For example, COVID-19 has impacted all our lives, devastated many economies, changed our social habits. In addition, the world faces existential challenges, two of them, climate change and environmental sustainability. If we are to have any opportunity or any hope of overcoming these challenges, we need fresh minds to think up novel solutions, consider out-of-the-box avenues, and be able to put together a coherent program. What GYSS has done is to enable these young minds to collaborate together, exchange views, and form a community which will give us some advantage in overcoming these issues. GYSS has done well the last 10 years. I believe that GYSS will continue to do well and will continue to engage our young researchers and inspire them to do great things. Congratulations to GYSS on your 10th anniversary. I believe GYSS will continue to be relevant and will create new challenges and opportunities for all our young scientists and benefit the world and the scientific community. Congratulations.
Hello, everyone. I'm Liu Zheng from MSc NTU, and today I'm also the host of this session. We are very honored to invite Sir Konstantin Novoselov to give us the plenary talk on the future materials. And Sir Konstantin received master's degree from the Moscow Institute of Physics and Technology in 1997, and he received PhD degree from Rambam University, Nijmegen in 2004. He is now a distinguished professor in the National University of Singapore. He is a Nobel laureate in physics in 2010 for his groundbreaking experiment regarding two-dimensional material, graphene. And in addition to this, he also won the Fellowship of Royal Society, Foreign Associate of US Academy of Sciences, and many others. Now, let's welcome Sir Konstantin to take the stage.
Good afternoon. Thank you so much for the nice introduction. So it's been really really a pleasure to work with you over the number of years, and it's a pleasure to be here today as well. So I gave a talk at the GYSS several years ago. It was most pleasant experience. So I'm back, and I'll try to update you with a few things which are happening in our lab, but also in the generally in the world in terms of new smart materials and designer materials. So, but probably a good place to start is graphene. Sorry about this, not because necessarily graphene is the future, but it's really it provides quite a nice platform for designer materials. So many of you do know what graphene is the thinnest possible material, only one atom thick, very simple, consists only of carbon atoms, and yet it has a number of superlatives, like it's the thinnest possible material, the strongest, most conductive, thermally conductive, impermeable, and so on. And because of that, it has been proposed to be used for a number of different applications, ranging from composites to biosensors, from flexible electronics to energy. And indeed, so although it's quite a special material in terms of science, we've been playing with it for a number of years now, and keep supplying us with new exciting phenomena up to now. It's actually, in terms of the applications, it follows quite nicely the footsteps of many other advanced materials before it, and I'm sure of advanced materials after it. So it started its way into applications from the simple applications in composite, mainly in sport goods. So ourselves, we worked with Richard Miller and McLaren to create this world's lightest watch, and then we used graphene panels for the composites in those sport cars. Actually, not for the sake of the strength or lightweight, but for the sake of the thermal conductivity, which allows you to speed up the process of production. And then and actually these days, most of the Ford models do use graphene, again for quite interesting applications of noise absorption. From the hindsight, you would probably guess that having lots of interfaces in the 2D composites would allow you efficient scattering of the phonons. And then from noise cancelling to noise creation, there are several companies which are working on graphene membranes for the headphones. So this is the example from the Aura. It's a company in Canada. So what you need here is the lightweight, but also extremely stiff material, and that's all graphene. And then go into more electronic applications like thermal spreaders, which is used by Huawei. And interestingly, graphene is now the material of choice for the quantum resistance standards. And for example, NPL in London do use graphene for the quantum Hall effect. So, and then these days, electronic applications start to be more and more dominant. So there are companies which produce extremely sensitive photodetectors based on graphene and quantum dots. And if I need to predict, then telecommunications would probably be one of the most interesting areas of application for graphene, but also for many other 2D crystals. And actually, personally, I think what is really exciting about graphene, that is the thinnest possible membrane, and we need to investigate this direction of research and applications much more strongly, because it's, of course, it's impermeable for any atoms, but at the same time it can be made permeable for some specific species, so we can use it for selective membranes, smart membrane applications. So that's basically been work for around graphene and in terms of science and in terms of applications for a number of years. Of course, it all won't be possible without advances in mass production and the technology of graphene as well, because we started long time ago with the Scotch tape exfoliation production of graphene. When you take a piece of graphite, it's the material which you find in your pencil, and then exfoliate it with the Scotch tape. However, of course, it's not really mass production friendly method. These days, however, there are many other ways how to produce graphene in large scale, depending on the quality you want to achieve and the price you want to pay. Starting from liquid phase exfoliation is the technique which is really good for such applications as coating, composite, energy, biosensors to CVD production, which gives you the electronic grade material, as well as some other niche way of epitaxial graphene production. However, this is just the beginning of the story, because if you like, you can ask yourself a question. Okay, if I use Scotch tape and I exfoliate graphite in my lead pencil, I get graphene. What happens if I exfoliate other pencils as well? And the answer is yes, you can do it. And actually, if you do it, you can produce many other one atom thick materials, two-dimensional materials, which would have which are similarly thin as graphene, but will have completely different properties. So these days we're talking about not only about graphene, but we're talking about the whole family of two-dimensional crystals which are available to us. And there are many dozens of members in this family, and actually our host today is the expert in the preparation of those crystals. We can discuss it later during our question and answer session, but that really gives us a lot of new opportunities. Well, first of all, because it gives us the opportunity to study the properties of those two-dimensional crystals, because physics in two dimensions always different from the physics in the three-dimensional crystals. And now we have two-dimensional insulators, two-dimensional semi-metals, semiconductors, conductors, ferromagnets, superconductors. So the physics itself is extremely exciting, what you can find in those materials. But also it gives us quite an interesting opportunity. And here I would like to diverge a little bit and just give you a bit of a motivation. Why do we need to seek new opportunities in terms of the material science? So generally, you would know that materials are extremely important for the development of the humankind. So we even call the ages we live in by the names of the dominant materials. Like there is the Stone Age, there is the Iron, the Bronze Age, the Iron Age. And a good question would be, which age do we live in now? And probably for the first time in history, we have quite a choice, because we can call our time the digital age, or the silicon age, maybe nuclear age, because most of the electricity we produce is now from nuclear. But it's important to make a smart choice, or maybe we don't need to make a choice. Maybe it's actually wrong to bet only on one material. Let me give you an example. Here is the periodic table of elements which we use in our silicon technology prior to 1990. So those very simple technology. So it's silicon, boron, phosphorus for doping, aluminum for interconnects, hydrogen, oxygen for passivation. That's it. So very simple technology. Even I could probably understand. Then we added some, later we added some copper for interconnects. We had to add a few other materials to provide the diffusion barrier, the work function matching material for the contacts, but still manageable technology. These days, we basically use more than half of the periodic table for in our silicon technology. And the situation is quite bizarre, because if I show you that there are less elements in our own body than we use in the silicon technology, and you would guess with me that our cells, we are much more versatile than our silicon chips. So, and that's quite a common problem, because we only bet, as human beings, we only bet on a few materials in our technology. So our electronics is all silicon. Construction, it's based on steel. Space engineering, it's the aluminum, bit of titanium. So a few materials means that we limit our opportunities to those few. If the electronic engineer needs to create a new system, a new device, he or she would need to look at the tables, what silicon can do for me, and then design a new device within those restrictions of the band gap work function, band gap of the silicon oxide, and so on and so on and so on. Ideally, of course, you don't want those restrictions. You would like to have material where you can vary all those parameters, and those materials do exist. So we call them the composite materials or the heterostructures. So we use them in our electronics and in construction and in airspace, but still there are few and far between examples of those composite materials. Ideally, of course, you want to create material from scratch by atom or layer by layer engineering, and then you would be able to design a material according to your needs. And that's actually exactly what we have now with the two-dimensional crystals, because of course we have a full library of those materials. Those are available in their monolayer form, but now we can go back into 3D and create a heterostructure of materials according to what we need, to what kind of properties or functionalities we want from those crystals. And indeed, it has been realized, and many groups in the world do work on this technology. It's called layer-by-layer material engineering, or Van der Waals technology, and quite a number of really exciting phenomena and interesting devices have been created using this technology. So here is an example of such a quite a complex device based on this technology. It's a light emitting diode. So you apply voltage, you get light out of this structure. So graphene plays only secondary role as a transparent conductive coating here. So the major part is played by those semiconducting quantum wells. So, and that's all great. And maybe I just spent 5 minutes of just to update you what is the progress of the last couple of years in this area, because what has been realized that those heterostructures are quite unique, because we can control not only the sequence of layers which we are putting together, not only the number of layers of each individual material, but also how we rotate those crystals in space with respect to each other. And what people realize that if you rotate crystals in space, their electronic structure, their Brillouin zone also rotate in space. And then if you allow hybridization between those electronic structures, you can gain really exciting properties, new exciting properties out of it. And that's indeed has been the breakthrough by the MIT group, who demonstrated that in a very simple setting, just 2 layers of graphene, when you rotate them, you can get such phenomena as superconductivity or ferromagnetism or mode insulation. So the ferromagnetic structures has been produced in twisted monolayer bilayer systems. And these days we basically, so it's quite an interesting the direction of research, how to control the properties and the functionalities of those crystals by orientation. We simply take the same material but twist them on the different angles, and then we get new properties out of it. For example, you can take boron nitride, which is the insulating counterpart of graphene, and if you rotate it, you can produce a ferroelectric material out of it. So with quite a microscopic ferroelectric domains. Or there was quite a bit of work on the production of the transition metal dechocagonites, and then if we have high quality niobium diselenide crystals, and if we twist control them, we can get new superconducting states within those twisted regions, and those new superconducting states is because of the Moore pattern and the different stacking between the different parts of those superconductors, which form an array of the Josephson junctions. So that's really gives us fantastic opportunity in creating new materials on demand, materials with the predetermined properties with the properties which you won't be able to obtain otherwise through any other means. So that's already great, and that's already gives us really a nice platform of getting tailored materials. So now we can produce on-demand properties for any new applications. But also we would like to go a little bit beyond that, and I would like to spend 10 minutes maybe to telling you what's the future of materials as we see it in our labs. That I don't think that simply predetermined materials with the predetermined properties is enough. I think we need to have much more from our material world than that. I think we need to have smart material. And again, let me just do a little bit of the diversion, a little bit of the background. I would like to just to say that we also a bit of the background here. So I guess many of you do remember this movie, the Terminator. So this movie was shot in 1991, and it was about this robot which traveled back to 1991 from 2029. So that's how we thought our robots in 2029 would look like, made from liquid metal, agile, changing shape, self-adapting, self-healing, and so on and so on and so on. So we are in 2022. And that's the robots which we've got these days, and I guess you would agree with me that the reality, we're a little bit outside of where we want to be in 2029. It's still okay. We still got 7 years to go, but unfortunately, I've got bad news for you that unless we change the very attitude to our technology, we won't be able to arrive at those liquid metal robots and in 2029. And the problem is really with the very attitude, with the very basics of our technology, which uses the so-called top-down functionality. So because individual parts, the materials which we use, they're not functional. The functionality only comes when you assemble those individual pieces all together, and then they gain functionalities. And that's not only about the clockworks or about the robots. It's about many other technologies as well, like in electronics and membranes and energy and so on. Our technologies start to be functional only once we assemble them into the system level. The situation is actually very different in biology, where in the biological systems, the functionality is distributed across many different levels. So individual proteins or viruses, they're functional in their own respect, membranes, cellular level, organ level, our body. So the functionality is distributed, and that's exactly why we're so efficient and so versatile. And that's exactly what we want in principle from our materials, that they would be functional and intelligent on their own, in their own right. Functional means that they can be programmed to perform a complex response to external stimuli, and intelligent that they would have memory to learn for a particular function. So let me just give you an example of such materials. So I told you already that you can make a nice membrane, siphon membrane from graphene, and you can make it, for example, for water desalination. But at the same time, we can actually, if we combine it with some other materials, you can make it into a smart membrane, which would be able to sense the conditions of the water which is passing through. The moment it senses the contamination, those parts would change their configuration and would close the pores and then stop the water flow. And that's what we want from our system. So here is another example. This is from colleague of mine in NUS, Guy Bazin, who works on the conductive polymers in conjunction with the live bacteria, and they grow together. And bacteria, during their metabolism cycle, they can emit electrons, which is collected by the conductive network, and it's a self-adaptive developed system which you can use as a battery. But basically, it is based on live bacteria which grow together with the conductive polymers, and that's exactly what we're trying, the idea which we're trying to push into other areas of technology as well, like neuromorphic computing, smart membranes, smart energy, and so on. Unfortunately, it's not that simple, because the moment you start to demand memory functions from your material, you immediately need to have out of equilibrium systems, so systems which can develop and switch between different states, and that's not what we are good at. So most of our physical approaches, they're based on the equilibrium conditions, and then we apply perturbative schemes to study out of equilibrium phenomena. So, and that's exactly what we're trying to do, is to figure out how can we describe those functionalities, which are properties which evolve in time, and how can we predict the structure of the material to give us the specific functionalities. So we do understand the basic principles. How can we create such materials? So they should be created based on strong interactions between components, and those interactions should go through multiple different channels, and then you should be able to get a degenerate energy landscape. And degenerate energy landscape means multiple minima, so it means that you can trap your material in one state or another, and then controllably move between those steps. Very similar to the folding and unfolding of proteins. So the reason our proteins are so versatile, so efficient at performing multiple functions, is exactly because they can be assembled into different configurations, and the energy landscape is extremely degenerate, so you can easily transfer from one minima to another. So we basically work now not with low dimensional material. The reason we need low dimensional materials, because when you put two materials together, two bulk materials together, they only interact at the surface. They don't interact through the bulk. So we want to avoid that. We want strong interaction. So we work with 0D, 1D, 2D, some 3D materials without bulk, like morphs and covs, and then we assemble complex heterostructures out of it in such a way that they would be responsive to external stimuli, but also would have some feedback to change their internal configuration as well. And based on these principles, we really try to apply it for a number of different applications. Let me skip this. And I probably just mention a couple of those existing applications which already exist. So one the most efficient way is to produce the heterostructures based on 2D materials and polyelectrolytes. 2D materials give you quite a predictable response to lights or electric field, and polymers, especially polyelectrolytes, they're very sensitive and selective towards the environment. And then if you create heterostructures based on those materials, you can tune it for a particular response, for a particular stimuli, but also you can make them to change their internal conformation upon a given stimuli, so it can be a smart material. So we used it for ion separation, we're trying to use it for drug delivery. We also make them into self-healing material that you can scratch it and then expose to a certain stimuli, and then it would heal itself in their own right. So here is another example. The work which we're doing in collaboration with Zhong and Liu, and it's a high entropy alloy, but basically the idea is exactly the same, that we store this material in a metastable state, and then upon if you make a defect inside, you can make it to self-heal and then self-adapt and grow back. And that's all due to the smart navigation or in the energy landscape and the direction of the entropic part of the free energy. So I think I would stop here, and I will say that materials which can be programmed in terms of their properties, but also which can be made functional and adaptive, is the future of the material science, and it would give us an opportunity to completely revolutionize many areas of our technology. So thank you so much, and thank you so much for your attention. Thank you.
Okay, let's thank Kostya for this fantastic talk. Here, I'd like to put up the first question. So as you have discussed in your slides, right? You give us a very pleasant journey, material journey from the single graphene to multiple 2D materials, and then we go to the complex functional intelligence material, right? We can do more and more now. More and more functions can be realized. So I believe the audience may be keen. What is the key challenging or key challenges in this complex system?
Well, of course, well, it's indeed very exciting to work with those materials. Unfortunately, at this moment of time, we're really only starting to create those complex heterostructures, and we have to work on our basic physical intuition. So you can guess, sometimes correctly, sometimes incorrectly, what the properties of this or that heterostructure would be, but it's still very challenging to predict exactly through our theory methodologies what's the outcome of those structures will be. So that's I think that's the major area which we need to improve, and we work a lot on the applications of AI towards the material science, and that's I think that's quite a promising direction, which would allow us better, larger throughput calculations on the complex materials. And generally, the origin of complexity and the moment when maybe there is a moment when you cannot predict at all the properties of those materials. So that's the origin of complexity, and maybe that's the origin of living materials as well.
Okay, thanks, Kostya. We got a lot of echoes from the audience. Here, let me see. This question is about the 2D material. For how likely are 2D materials to be adapted for nanomedicine, for example, drug delivery, cancer detection?
All right. Well, I should say that of course there are lots of work and lots of studies in terms of the applications of nanomaterials in general and 2D materials in particular for different nanomedicine applications, either drug delivery or smart sensors or oncology therapies. So there are it is definitely on the agenda. generally, and what I see in the literature, at least in the research, there are many exciting progress there, and there are a number of startup companies in different areas. The problem is that, of course, medicine is extremely conservative area, as it should be, because you don't want to produce any harm, and unfortunately the interaction of biological systems with any objects on the nanometer scale is still very badly understood. So understandably, it goes at its own pace, but at least in terms of research, it looks extremely promising.
Okay, many thanks. One more question is about the graphene. If two layers of graphene show interesting properties, so what's about increasing the number of stacks? Could it show new property? How many stacks of graphene that can act as for 2D materials?
Right. So okay, that's so the it's a good question, and it's a valid question, of course, and we loved graphene for, and we still love graphene for its simplicity, that you can produce very predictable result once you understand it. But indeed, two layers, especially twisted, produced very new phenomena, and we do study 3-layer, 2+1, 2+2, and so on, and they all show very exciting physics. The problem is that it's the complexity increases as well at the same time, and the naive and very hand-waving understanding is not always possible once the complexity increases. So just to give you an example, if you take 3-layer graphene, so you got a semi-metal. However, if you shift the top layer by half of the unit cell to so-called ABC stacking, you would immediately get a topological insulator which is an insulator with the surface state. So it's extremely rich area, and in terms of study of the physical phenomena of the many-body physics, it's extremely rich, and we still work a lot on it in our lab, but actually in many labs across the globe. And I think we will still see quite a lot of breakthroughs from such systems.
Yes, I agree with you. Actually, instead of stacking, we can also twist it.
Well, yeah, that's so.
Kind of system.
Yeah, that's really powerful technique, and so it's quite surprising that what's now good 15 years down the line, a material as simple as graphene still, and we're still playing with it. So,
okay. Here the interesting question about quantum computing we just discussed, right? Dear Professor Kostia, may you explain whether there is a chance of employing 2D magnet van der Waals material as a potential application in quantum computing?
Oh, okay, that's something very new. So, of course, you know that. So there are several competing technologies in quantum computing. They originally started with arrays of Josephson junctions, now switching more towards cold atoms, and that's and the reason for that is the reproducibility, that it's very difficult to create identical identical Josephson junctions. So the what I showed you today, arrays of the Josephson junctions due to Moira pattern can be, I mean, it's difficult to control them in its own right, but at least you got the these arrays of the identical Josephson junctions. So it's the crystal of Josephson junctions. In terms of the magnetic materials, of course you can get unusual magnetic states and correlated states as well. Personally, I'm not aware of the proposals of using 2D materials for the quantum computing, but again, it's not exactly my area of expertise. So I'm sure that we will see very interesting quantum correlated states in 2D magnets, in heterostructures of 2D magnets, in twisted 2D magnets. Going towards quantum computation is the next step. So I cannot comment on that.
It's in the near future. So the following question is: have people used smart material to aid the development of practical quantum computers?
Well, not yet. As I said, there are several leading directions in terms of the of quantum computers and the technologies for quantum computations. We're trying to use quantum computers for to model those complex materials. So that's a different direction. And just as is the so-called quantum simulators. There haven't been any proposals on the use of the smart materials for quantum computers, but as I said, there are definitely very untrivial quantum states which we can create and develop in many different heterostructures, either graphene or twisted superconductors or twisted ferromagnets. So the correlated states are definitely can be very of very unusual nature. How to control them and perform quantum operations? That's a difficult question, but I cannot say definitely no for that.
Okay, thank you. A question about the commercialization. Okay, although there is a lot of research on graphene, commercialization still far off. Why this commercialization technology gap, and why so much research on graphene has been abandoned?
Well, I won't immediately say that it is not there. Of course, there was like maybe 7-8 years ago there was a hype on the applications of graphene, and we thought that one day we just wake up and everything around us would be made of graphene. But that's of course a very naive picture. Actually, you probably have more graphene in your life than you realize. So like most of the mobile phones by Huawei do use graphene. So graphene is being used by hundreds of tons for batteries applications, for photo detectors, and so on and so on and so on. So you probably do come across graphene every day, several times. It's not a revolution; it's a quiet evolution. But that's generally how things are in this area. And of course, what people need to realize that unfortunately getting exciting research sometimes, or let's say putting materials into technology can be sometimes more difficult than making exciting research, because and that's exactly the problem which I addressed before, because you have to retrofit everything. So your new devices needs to be compatible with with all the previous technologies. And you cannot imagine how many restrictions our silicon technology is giving to us in terms of the temperature range, the vacuum level, the type of materials, and so on. So I would disagree that it is behind in terms of applications. It goes exactly at the pace of any other new materials which have ever been introduced into technology.
So actually, this question remind me application about graphene. That is cell phone. So graphene has been using cell phone to cool down the cell phone.
Yeah.
Yes.
It's quite surprising that made from individual flakes, it still has the thermal conductivity higher than any other materials available to us. So it's fantastic application, and I'm sure that we will see other areas where it is being used.
Yeah, exactly. Okay. One more question is about MAXing. Have you heard about MAXing and its potential?
Yeah. So MAXings, of course, that's those are great, also two-dimensional materials produced in a different way. Personally, I don't work on them, but I do follow the literature, and it is being used quite widely for, or at least tested quite widely for battery applications, for supercapacitors. So I don't think that the future belongs to only one material, and I hope not. I hope that we will be using combinations of different materials. So MAXings are quite natural part of those future heterostructure materials.
Okay, thank you. Maybe I can use this last question to wrap up our session. As you, when you got the Nobel Prize, right? You are very young. If I remember correctly, it's 38, 37. So among one of the youngest Nobel laureates, do you have any message for the young generation, like the audience?
Well, I always would like to suggest to people, the only one thing is that don't listen to any suggestions. Just follow your own way. It is important to be excited about your own research, and then I'm sure that you will get to a success. Even though it looks like we understand everything, in fact, once you start getting into details, there are so many new things to be discovered about any system. So just be excited about what you are doing, and then I'm sure that you will get to a success.
Thank you very much.
Thank you,
and thank you all for the audience. I hope you enjoy the talk. Okay, thank you.
Thank you.
Ladies and gentlemen, a warm welcome to GYSS 2022. It's my great honor to invite Professor Stefan Hell to give a seminar entitled MINFLUX and MINSTED Provide Molecular Scale Resolution in Fluorescence Microscope. Allow me to introduce Professor Stefan Hell. Professor Stefan Hell is a director at both the Max Planck Institute for Biophysical Chemistry in Göttingen and the Max Planck Institute for Medical Research in Heidelberg, Germany. Professor Hell is credited with having conceived, validated, and applied the first viable concept for overcoming Abbe's diffraction-limited resolution barrier in a light-focusing fluorescence microscope. For this accomplishment, he has received many awards, including the 2014 Kavli Prize in Nanoscience and the Nobel Prize in Chemistry. Professor Stefan Hell received his doctorate degree in physics from the University of Heidelberg in 1990. From 1991 to 1993, he worked at the European Molecular Biology Laboratory, followed by stays as a senior researcher at the University of Turku, Finland, between 1993 and 1996, and as a visiting scientist at the University of Oxford, England, in 1994. In 1997, he was appointed to the MPI for Biophysical Chemistry in Göttingen as a group leader, and was promoted to director in 2002. From 2003 and 2017, he also led the research group at the German Cancer Research Center. Professor Hell holds honorary professorships in physics at the University of Heidelberg and Göttingen, and his research has inspired many people, including myself. So without further delay, let's welcome Professor Stefan Hell, please.
Thank you very much, Dr. Liu. It's a pleasure to be here and speak about the latest development in what is called fluorescence nanoscopy or super resolution fluorescence microscopy. I'm sure you know that throughout the 20th century, it was widely accepted that the resolution of any fluorescent microscope is fundamentally limited by diffraction to about 200 nanometers. And the best, say, contrast modality or resolution for that matter was achieved by the so-called confocal microscope. But things changed at the turn of the century, of the 21st century, when STED microscopy was invented and developed, because STED microscopy showed that it's possible to come up with a physical, say, method that fundamentally improves the spatial resolution, gets a higher spatial resolution up to roughly a factor of 10. So from 200 nanometers down to about 20 nanometers. And just as you've heard from Dr. Liu, this has led to a Nobel Prize. And what I'm showing here is actually the official poster of the Nobel Foundation at the time the Nobel Prize was awarded in 2014. And it shows the concepts that share the prize, namely STED microscopy, which here is sketched having a beam that turns molecules on. The green beam turns fluorescent molecules on so that they emit fluorescent light. Then there's another beam that turns fluorescent molecules off. It's shown here as a red donut-shaped beam to confine those on-state molecules to the center of that beam. Then, of course, by scanning with those beams across the specimen, you separate the molecules by sequentially turning them on and off if they are too close, if such that they are separable. Now, I had the honor of sharing the prize with Eric Wetzig and W. Myrna, and Eric Wetzig demonstrated for the first time that you can up with a variant of this on and off modality, where not say groups of molecules are turned on and off in a certain regions, like defined by a donut, but molecules are turned on and off individually. So the mechanism for separating molecules is the same in PalmStorm and instead, but the way it's done is somewhat different. Now, what it's also similar in both of these concepts is that both have the capability of attaining a spatial resolution that is truly at the molecular scale. So in theory, so each of the two methods, both STED and Palm or Storm, can attain a spatial resolution that is able to separate molecules even if they are as close as the size of the molecules themselves, so a nanometer, 2 or 3 or 4. Now, that's just in principle, but in practice, at the time the Nobel Prize was given, if I may say so, the resolution wasn't better than 20 nanometers. So it was not possible to get higher resolution improvement factor than a factor of 10. And so the Nobel Foundation actually put it quite correctly here in this poster. The microscopes crossed the threshold, which was the diffraction barrier. And what I'm adding here is that, but they did not attain the ultimate limit. And therefore, the major recent goal in my lab in the last, say, few years was to get to this ultimate limit. So the goal was attaining a molecular size 3D resolution of, say, a 1, 2, 3 nanometers that is at the size of the molecules itself. And this was, of course, a big step because it meant that we had to improve the resolution by another factor of 10, because as I said, at the time the Nobel Prize was given, the resolution was only at about 20 nanometers, and only in very rare exceptions you could get a spatial resolution that was better. Now, explaining the situation. Now, let's assume we have an array of molecules which looks like this, and each of these little stars are molecules. They are 11 nanometers apart. So the reason why one could not tell them apart at sub-diffraction distances in general was the fact that it was not possible to address them individually and also find out their position individually. So neither Stead nor Palm could do that. And if you have this problem, of course, they all light up at the same time, and the signal is confused and confounded. So the key to separating them, and this is really the essence of the whole field, of the whole super resolution field, is that you manage to turn them on and off. So this is the way the molecules are separated. That applies both to Stead and Palm Storm. You need a mechanism for making them emit sequentially, so to speak. And here, for example, it is shown sequentially on a single molecule basis, as it is usually done in Palm Storm. And there are several mechanisms of turning molecules on and off. You could do de-excitation by stimulated emission. You could do a cis-trans photoisomerization, electron transfer, and so on. But just remember, in order to separate them, to distinguish them, on and off is the key mechanism that has enabled the development of the field and that has been used so far. And so far, no other, say, effective mechanism has been identified that can separate molecules so effectively as an on-off transition. And of course, if you turn them on and off separately, then you can distinguish them. But it doesn't mean that you know where they are. And if you go back, for example, to the Palm principle, the Palm concept could not resolve molecules that are, say, 11 nanometers apart, simply because, and this is shown here in a recording, because although the molecules were turned on and off individually, the position that needed to be defined after the molecules were turned on and off could not be defined better than with a sigma with an uncertainty, so with standard deviation of, say, about 15 or 20 nanometers. And this is why one could not know where the molecules really are. And therefore, if the signal from a single molecule was detected, you could not tell if it's this one or that one or that one, because they all fall within this uncertainty. And that's the reason why this image of this, say, array of molecules was blurred. And so one way of addressing this problem and getting to a higher spatial resolution is to revisit the way the localization of individual molecules was actually done. And now I'm explaining you how people thought that molecules had to be localized in the past. Now, usually people localized molecules in the following way. They had an epifluorescence microscope where the whole field of view was illuminated with excitation light. So this is the green light. And the molecule, for example, is this little star. And then this little star fluoresces. It produces fluorescent light, which is directed here to the camera. And then, of course, the camera has pixels, and it produces this diffraction blob on a computer screen. That is, this diffraction blob is due to the fact that the fluorescence light is here diffracted on a camera. And then localization meant actually to find out where the molecule is located, of course, in the sample plane. And this is done by calculating or finding out the centroid of this emission pattern, of this fluorescence pattern, because the center of this fluorescent pattern, of course, must correlate very strongly by geometrical optics with the position of the molecule in the sample. And of course, if you calculate that centroid, you will have a certain uncertainty still, and that uncertainty will depend on the number of fluorescent photons, because the more fluorescent photons there are on the camera, the more precise will be the calculation or the finding out of the position of the molecules in the focal plane. So it scales, as you see, inversely with the square root of the number of detected fluorescent photons. Now, this is what people thought has to be the way molecules are localized. And they didn't think really about other ways, effective ways of localizing molecules. And the reason why I was motivated looking into this problem was that this is actually a principle that really is photon greedy. So it needs to maximize the number of fluorescent detection. But maximizing the number of fluorescence detection, the number of fluorescent photons is a problem, because usually fluorescent molecule bleach, so there is only a limited number of detections, and that you have to wait for n to get large, and that takes time, so it's slow. And then there is another problem that you will appreciate if you have a physics or physical chemistry background. The emission of a molecule is a dipole emission, so to speak. And then, of course, the pattern here that you find on a camera will shift in the focal plane if the orientation of the molecule changes. So the dipole orientation is a serious problem that leads to, say mislocalizations or shifts, systematic shifts that give us in the end a wrong position of the molecule. And since this concept, of course, has serious limitations, it was worthwhile considering a new way of localizing individual molecules, a new way of finding out where the molecule is positioned. Now, the rationale is very simple. Of course, you need many photons in order to localize a molecule, because a single photon could never be used to localize the molecule, simply because a single photon is diffracted somehow, is shifted somewhere within the diffraction zone, goes somewhere in the diffraction zone. So you need a pattern of photons, many photons, to find where they are. But using a fluorescence pattern is, of course, not very clever in a way, because, as I said, the number of fluorescent photons is limited. So why not using a pattern of photons that is from the laser, that is coming from the laser? Because there's plenty of laser photons available. So laser is very bright. There's no problem getting enough photons. And this is actually the rationale behind the concept that I'm talking about now. It's called MINFLUX. And it uses, for example, a donut for identifying the position of the molecule. And this is, of course, if you will, lent from the concept of STED microscopy, because in STED microscopy, the donut defines the position of emission, as I explained to you in the beginning. And so this idea of defining the position of emission, of targeting a certain coordinate in the sample space, is taken actually from STED. Now, so what do I mean? So if we use a donut beam for excitation, and if you have a donut pattern, then of course we can very effectively target a certain coordinate in the sample space at will. Because the zero here of the intensity of the donut precisely defines the position in the focal plane. And not only that, we can shift this position of the donut around with a beam deflector with very high precision, because that's no problem shifting a beam around with the angstrom position in the focal plane. And of course, we can define this position of the zero also, if you will, this angstrom position, because we have plenty of photons coming from the laser. And then once we have defined the position in the sample space, the only thing we have to do is we have to relate the position or the unknown position of the molecule with the known position of the donut. And of course, if we find out the distance between the two, we know where the molecule is, because we know the position of the donut. That's perfectly controlled by the electronics of this beam deflector. And so how do we know how far the two are apart, the zero of the donut and the molecule? It's very simple. If the two coincide in space, then there is no fluorescence emission, because here there's a zero beam, a zero intensity of the excitation beam, and so there's no fluorescence emission. If it's slightly away, if the donut is slightly away from the molecule, there will be some emission, and it's very clear that the brightness of fluorescence that we will detect here at the detector will depend on the distance of the molecule from the donut, or the donut zero from the molecule for that matter. And so we don't use a camera here anymore. We just use a confocalized detector. And then we try to figure out where the molecule is just by measuring actually the distance between the donut zero and the molecule. And now I'm explaining to you why this concept is so photon effective. In order to make this clear to you, I have introduced a little demon, okay? And demons are, they do not exist in reality, but at least in thought experiments, you can come up with a demon that knows something that we humans don't know. And in this particular case, imagine that the molecule starts moving and the demon kind of guesses where the molecule goes. What can the demon do in this case? It can shift, using this beam deflector, it can shift the donut around in such a way that the excitation intensity zero always coincides with the fluorescent molecule. But the molecule in this case will not fluoresce. Why will it not fluoresce? Simply because it is coinciding with the excitation zero. Yet, the demon would perfectly know the position of the molecule because it controls the position of the donut, and the position of the donut must coincide with the position of the molecule. So the thought experiment tells us that in the limiting case of the existence of a demon in this case, one could say precisely localize the position of the molecule with arbitrary precision, so with angstrom precision, without requiring any fluorescence emission, because in this case, the molecule doesn't emit. And so this is really totally contrary, opposite to the previous concept of localizing molecule, where the emphasis is placed on the fluorescence emission pattern. Here, the emphasis of localizing is placed on the excitation pattern. So we put the burden of requiring many photons for localization, not on the fluorescence emission pattern, but on the excitation pattern. And excitation pattern, photons are cheap because they come from the laser. And not only that, you can imagine as a first rough guess that if you do it like this, there will be no wavelengths dependent. So the localization precision, unlike in normal localization as it's used in Palm Storm, will not depend on the wavelengths. Why? Because we're just matching 2 points. You know, there is the donut zero that is a point, and there is a, say, fluorescent molecule that is a point. If you just match 2 points, it doesn't really matter with which wavelengths, so green or blue or yellow or red, this excitation pattern is actually made. Now, in reality, there is no such thing as a demon, but you can approach the situation sort of by replacing the demon with a controller. You have a controller here, and there's a photon detector, of course, that feds the number of detections into the controller. And now, if the molecule, so to speak, starts moving, we would detect fluorescent molecules simply because the zero does not always coincide with the position of the molecule. But we know that the more detections will be seen here by the detector, the further away the molecule is from the position of the zero. And so we shift again using this controller the zero of the donut excitation beam onto the molecule. So in other words, we can use we can measure actually the position of the molecule very effectively with very few emissions, simply because we only have to measure the distance, the residual distance between the position of the molecule from the position of the donut zero. And this means that we need much fewer photon emissions than is usually the case, because the large part of the localization is done by the photon from the donut, and only the residual distance has to be measured with the fluorescence. And now I'm explaining to you how we actually find that out with the controller, the position of the molecule. And this is actually not very, very difficult. I'm showing a very simple situation, which actually explains the basic benefits of this concept. Let's assume the molecule is actually within this range here. And so we don't know that it's here, but we have to find out. So what do we do? This is the donut for excitation. Of course, this is the profile of the donut, okay? This is the profile. It looks like this. And here we map the fluorescence emission. And now if the donut starts moving, you see, once the zero of the donut coincides with the molecule, I'm showing it again. So the donut starts moving, okay? And you see now the zero of the donut coincides with the position of the molecule. Then the fluorescence emission is zero. It's clear because if the zero coincides with the molecule, there's no fluorescence emission. And then we know where the molecule is located. It must be here, at its position XM. And now you may say, okay, in order to find it out in this way, we have to scan very closely and densely the donut across the molecule. That's not the case, because if you know that the profile here of the donut is, say, has a certain function, and in the first approximation will be a quadratic function, then it's perfectly enough to measure the fluorescence at the two endpoints. And this is why I'm showing these endpoints in purple and in orange here. So it's perfectly enough to measure the fluorescence here at the position of the donut when they are in the endpoints and 0 and 1, because you can calculate with a simple say algebraic solution of a quadratic equation. You can simply calculate where the molecule actually is located. So within this quadratic approximation, where you assume that here at around the 0, the intensity is a quadratic function, which it always will, you can calculate easily that the position xm of the molecule is given by the distance L, where the molecule is assumed to be located. So it was assumed to be located within this distance, divided by unity plus the ratio of n, the square root of the ratio of n1 divided. Basically, this is the number of photons that are detected at the two endpoints. Again, you measure you measure here the fluorescence, measure here the fluorescence, then you can calculate where the molecule is. Now, it must be XM. But there's another interesting aspect that we can see actually from this equation. There is no wavelength dependence in here. This is very, very interesting. And then there is also no molecular orientation dependence. So in first approximation, here we can locate the molecule without having to worry how the molecule is oriented in space, contrary to the normal localization, which is done in Palm Storm. Now, the precision with which we get a position of the molecule, and that's interesting, scales now with L, with this range L. And this is very, very useful because we can do it in an iterative way, the finding of the position of the molecule. We can do it such that we first measure roughly where it is, then we have a coarse approximation, but then once we have the coarse approximation, we can reduce this distance L. We can zoom in, so to speak, on the molecule, and then the precision will go up. And this is, of course, more effective. Reducing this L is more effective than waiting for more photons to come. So in a normal localization, as it's done in Palm Storm, you have to wait and wait and wait to get n larger, but that's ineffective because it scales only with the square root. So that takes a lot of time. So you need 100 times more photons in order to get only a 10-fold improvement in resolution. But here, if you decrease L, say 100 times, you get 100 times improvement of precision. And so it's always more effective to reduce L than to wait for more photons. And so in other words, once you have a rough estimate in the first step where the molecule is, you decrease the region where you look for it, and then the precision goes up automatically. So a way of doing that is to do it iteratively, just to look coarsely where it is, and then bring the zero, so to speak, closer to the molecule. And this reflects the basic idea with the demon. You have to bring the zero close to the molecule, and the closer you bring it, the smaller this residual gap is, the more precise you will be, the fewer photons you need. Now, this was just a single dimensional case, a 1D case. In 2D, you would need perhaps 3 points. It's better to use 4 points because it makes it more stable and more robust against, say, small, deviations or so, stemming from the fact that we are still recording photons that are subject to Poissonian statistics, but it doesn't change much. It doesn't really change much because, again, we have a precision that scales with L, and now L is not just a line, L is a radius because we look in 2 dimensions, and it's always more effective to decrease L rather than to wait for more photons to be detected. So as a rule of thumb, in practice, you can save 20 to 100 times detections to get the same localization precision. So 20 to 100 times fewer detections are needed in order to get the same precision as you would get with a normal localization that is done in Palm Storm. And this is why Now, using MINFLUX, we have been able to separate those molecules. Unlike in a standard palm storm case, now in the MINFLUX case, we can separate the molecules very precisely, and the precision that we get here is of the order of a nanometer, so the order of the size of the molecule itself. In order to separate that, we have to do an on-off transition, of course, of the molecules. Even 6 nanometer close molecules could be separated, as you can see in here. Not in Palm Storm, but now in MINFLUX, you can get the separation. Don't forget, and this is actually quite striking. Now, when I started the field, I mean, I said, well, at some point it will be possible to get down to the molecular scale. People really thought that I'm crazy. They said, oh, this guy is exaggerating. He will never get a job because he's making such ludicrous claims that are scientifically totally outrageous. But now it's true. If you can switch fluorophores on and off individually, you can now attain a molecule scale optical resolution of fluorophores, even with normal objective lenses. So it's not about changing the imaging modality. The key idea was to turn molecules on and off, of course, fluorophores on and off, to make them separable. And of course, you have to find out where they are. Now, fewer detections are needed now. This is why we get with MINFLUX. It's very, very high localization precisions, faster localization, and you have a negligible dependence on emission dipole orientation. This is why this method has become so successful. Now, for those of you who want to apply it to biological problems, the limits that are set now to the imaging are not set by the optics anymore or by the wavelengths or so. They're set by the labeling and the size of the labels. And this is not a physical problem. It is a labeling problem. It's a problem of, say, labeling chemistry or biochemistry, molecular biology, but not an optics problem. It's not a physics problem anymore. Can you take large fields of views? Yeah, of course, one way of doing it is you scan over large field of views and localize the molecules individually. And this is just an early result that I'm showing you now, where we looked at nuclear pores that were imaged on a, say, larger field of view. And again, a conservative estimate of the spatial resolution is that once you can separate the molecules individually, you can have a spatial resolution that is below 3 nanometers. So the precision, of course, in that case, will determine the spatial resolution. And now, if you zoom in on these nuclear pore complexes, it is actually quite revealing that you can get, say, localization clusters here that can be associated with individual molecules. And this shows that the molecule scale resolution has been reached. Now, this is that which won a share of the Nobel Prize. There's a factor of 10 in between the resolution of the two, and there's another factor of 10 from here to confocal. So between confocal, which used to be the gold standard in the year 2000, if you will, is now worse by a factor of 100 over what you can do now. So MINFLUX can do a spatial resolution that is 100 times better than confocal, and I'm sure this will be a big difference. And it's of course already making differences. Now, it can be done in the lifestyle conditions as well, if the molecules can be turned on and off. Of course, if they move very quickly, then it's difficult to localize them and the pattern will change. In this case, it's better to confine the field of view to small dimensions. Ways of getting the field of view up is to use many donuts or line patterns or something like that, which has advantages and disadvantages. And these are projects that will certainly be done, at least by somebody in the world. At this point, I would like to acknowledge the people who have contributed to this development, so either as PhD students or as postdocs. And this particular gentleman, Francisco Baltarotti, is now continuing his academic career. And here are the papers where everything is explained. But there's another point that I would like to make here. When I started this field, so of breaking the diffraction barrier and getting to a very high spatial resolution, ideally down to a molecular scale, I was driven just by curiosity. I didn't want to do something for the life sciences or something. But curiosity can very often lead to breakthroughs, and the breakthroughs was that you can overcome the diffraction barrier using a state transition and an off transition. And if you have a breakthrough, this always leads to economic value. And this is why realizing the need, of course, for such high resolution instruments, I set up with my students a company, and that's why I show the disclaimer. And they have actually managed to come up with a rugged version of this MINFLUX concept. So the reason why I'm showing you this is you shouldn't think this is just an academic game that can be done in a academic lab. You can also get a high spatial resolution under, say, normal lab settings. And you see here now the resolution in this commercial version is as good as it and in my lab. So it's a sigma of 2.2, and there is even a Z resolution incorporated in this case. Now you see the nuclear pores in 3 dimensions, and the spatial resolution in Z is of the order of 1.6 nanometers. And this again shows the huge progress that can be made, of course, just by exploiting a very strong principle and then doing the technological developments that are needed. In this case, of course, several points have been used. So 7 points in this case, 5 here in X and Y, and 1 above and below the focal plane. And the Z resolution, as I said, with a single lens is of the order of, say, below 2 nanometers. Now, not only you can image, you can also track faster because you need fewer photons to localize the molecules. And say, this is a new tracking record, if you will. Precision of 13 nanometers of molecular movements could be attained in only 234 microseconds, and the molecules can be tracked here. This is a labeled lipid on a membrane with very high spatial temporal resolution. Now, I think MINFLUX will benefit, of course, and its applications from this high precision that can be attained within a very short period of time. So it will be predestined for looking into molecular movement. So this is a big range of applications, and also a high optical resolution, as I have shown, will be a major strong point of this method. So depending on the fluorophore and on the sample background, the resolution will be of that order. So what about STED? So STED was the first concept that overcame the diffraction barrier. And some of you may think now STED might be totally outdated now that there is a resolution that is that good. That's not the case. So I would even say that the good days of STED are yet to come. Why? As I explained in the beginning, instead you have an excitation beam. You have, again, this donut-shaped beam that targets a coordinate in a sample plane. Okay, here's a 0. Then you have this region where fluorescence is allowed because the donut beam, in this case, doesn't excite the molecules, it turns them off. And so the molecules here are not able to emit. So we have here a 0 fluorescence zone. And now this can be used in order to mimic a situation like in MINFLUX. We can take this region where the molecule is allowed to emit and make it rotate like this. Let's assume the molecule is again here. And then, of course, this is the center of rotation. And now if you manage to, again, to make the center of rotation where there is no fluorescence emission or excitation coincide with the position of the molecule again, then we can localize, using this combination of excitation and STED beam, the molecule very, very precisely, like in MINFLUX. So in a way, the circulation, of course, emulates the donut-shaped beam that we had in the MINFLUX case. Now, you may say, now, why is this good? Why not just doing MINFLUX, and why doing what we call now MINSTED? The thing is, the STED beam has an advantage over MINFLUX. It keeps the background low. And say a conceptual limit, so to speak, of the MINFLUX concept is that the background, of course, will not allow the precise measurement of the position of the molecule if the background is too high. And here MINSTED has an advantage. And as you can see here, say 100 photons were perfectly enough, or 200 photons were perfectly enough to localize with a sigma of 2 nanometers. So this is even, the funny thing is, even more effective in a way than MINFLUX in practice. And this has led to very, very sharp images. So MINSTED images, as you can see here now, again, confocal as a reference. That then as a reference. And now the MINSTED images, if you look at them here, again, you get a sigma of 2.1 in this sample in the cell with 1200 counts. This is not much, and molecular scale resolution. Now, the good thing is now that with that, you can tune now from the diffraction limit essentially down to the molecular scale. And this shows that MINSTED, like MINFLUX, is definitely one of the very, very powerful methods in the future. So what are the applications in the future? Making molecular maps in cells, say, of the nucleus, of ER, Golgi, and so on, in 3D with the highest possible spatial resolution. And then, of course, also looking into molecular dynamics, so watching molecules move very quickly at small scales with the highest possible precision. In my view, there's no other method. I can't imagine right now another method that could detect molecular movements at this spatial temporal resolution as it is the case with MINFLUX or MINSTED. And with that, I'm thanking you very much for listening so patiently. Thank you.
Wow, Professor Stefan Hell, thank you for the wonderful talk. It's amazing to see that the resolution of a fluorescence microscope goes from 200 nanometer, then to 20 nanometer, and now it's only 2 nanometer. So maybe I'll start with the first question. So
Sure.
do you think is the upper limit for the resolution?
Yes, I mean, optically, as I said, there is, in optical terms, there's no limit anymore. So there's no fundamental physical limit that can, that put a, say, a very strict boundary to what you can resolve. However, there are practical limits in fluorescence microscopy, which stem from the fact that the fluorophores, of course, are only used as a proxy for the molecules that you usually want to see. For example, you want to see a certain protein, of course, in fluorescence microscopy, you don't see the protein directly. You see only the fluorophore that stands as a proxy that labels the protein of interest. And so you have to keep into, you have to take into account that the fluorophore has its own size. And of course, there is a distance between the fluorophore and the protein of interest or the molecule of interest. There's distance given by a linker or maybe a nanobody or something. So the actual limits right now are not optically, they are just given by the labeling procedure that is inherent to fluorescence imaging. So in optical terms, limits have all been sorted out. But of course, in labeling terms, there are practical limits for those who want to use the microscopes.
Okay, thank you. So I'll take the questions from the audience. There are a lot of questions coming now. So maybe the first question, at what point is a fluorophore itself going to be too big for the donut used in MINFLUX? Or is that not a problem at all? For example, the difference between looking at the GFP versus nothing mind fluorophore.
Yeah, I mean, typically the fluorophore, say the fluorescing part, so to speak, of the molecule in question is of the order of 1 to 2 nanometers. So that's the pi conjugated, say, electron system, and that, of course, probably will not be. You cannot make that smaller anymore, at least not for polyatomic molecules, and so so that is clearly say a fundamental limit. And of course, if you have molecules that are very close, say 2 fluorescent molecules, they will kind of interact with each other. They will exchange energy. There will be collective behavior. So at distances that are below 5 nanometers or so, there will be effects going on that are very specific to the fluorophores.
Okay.
But the donut itself, I mean, will not be a problem in that sense. What limits, so to speak, the use of a donut or of any intensity minimum is the fact that there is background. So there's always some background that kind of makes a zero not a perfect zero. So there will always be some DC level of light intensity that will not make it perfectly round. But but the good news here in actually in this research is that we can attain the maximum spatial resolution, say that is at the size of the molecule without requiring a perfect donut or something. So it works even in practice. So this is actually the good news, and if you will, the surprising news, that you can really get down to the molecular scale despite all the practical limitations of making donuts and the rest of it.
Okay, so here is another very interesting question. Thank you for the intriguing talk, Professor Hell. Do quantum effects play a role in the location of the molecule in your experiment, or are those a much smaller order of magnitude?
Yes, if you think about quantum effects, like okay, you apply the Broglie wavelengths to the molecule, so that is much smaller. That is very, very much smaller. And of course, the molecule is attached to the environment, like coherent effects with the environment, or so that won't play a role. So I don't think that plays a role. But of course, don't forget, quantum effects per se are used here in order to make this type of microscopy viable. Because in the end, what we do is we place molecules in two different states, like an emissive state and a non-emissive state, in order to make them separable. So without quantum mechanics, this whole thing wouldn't work. So at the time that the diffraction limit was discovered, there was no quantum mechanics. I mean, Ernst Abbe back in 1873 didn't know about molecular states and, of course, not about quantum mechanics. And that's why he would have never come up with a solution as we have come up. But now that we use, say the consequences of quantum mechanics, namely there are states in the molecule and transitions due to photons and so on. Because of that, we can overcome the diffraction barrier. So there is a lot of quantum in what I've been showing. But of course, the quantum effects that you are alluding to most likely do not play a role.
I see. Okay, so we come with a question with a sample preparation. So what are the limitations of MINFLUX? I'm wondering how to ensure perfect sample stability versus a minor sample drift without compromise the precision of the molecular detection.
Yeah, this is a very good question that come up in practice. Yes, in order to make the experiment viable, you have to make sure that you compensate for drift. And actually in all these systems, including the one that I've shown you that is commercially available, I would say the majority of the efforts actually went into making sure that that there is no drift, or if there is drift, it's detected and then compensated. So usually you cannot avoid drift. There will always be some drift, but you have to make sure that you detect it with very high precision and then compensate for the drift. So that definitely plays a role. But if you ask me about the limits are largely given by background, as I said, because you're detecting individual molecules in a dark region where you don't excite them. And of course, there will always be some background. And if you manage to keep the background low, and then of course you can do it quicker and more precisely for a given number of detected photons. So this is also why it's very advantageous to have a confocal pinhole, so a spatial filter in front of a detector, because that keeps background low. And this is why I believe that MINFLUX has many more applications in 3D imaging, where you have to go deeper into a sample, because you have this ability to keep the background much lower than in other, say, single molecule detecting methods.
Okay, thanks, Prof. So here is a question like Professor Hell, are you able to do live cell imaging experiment with MINFLUX, MINSTED, or will you be able to do it in the future?
Very good question. Live cell imaging, it has actually been done. So, so in one of the papers we've published actually in Nature Methods, there is an example where, live cell images have been taken actually from nuclear pores with labeled with a version of a fluorescent protein. Yes. As I said, the limit is that something is moving very, very quickly, and then of course you don't have the time to detect it. But again, MINFLUX has here an advantage over most other methods, simply because you require fewer fluorescent photons to find out where the molecule is. So can you do live cell? Yes. Sure, you can do it, and you can do it better than say with Palm Storm when it comes to imaging small regions. But keep in mind, of course, if it's moving too quickly, of course, then it's not possible to localize the molecule with the precision that you may want. But that's not a problem of MINFLUX or so. That's something that always exists. If something moves, of course, then you need fewer. Then you have to detect something quicker. That's very clear because there's little time.
I see. Okay, here comes another interesting question. Thanks for the fantastic talk, Prof. Hell. Do you think there's a potential for the combination of MINFLUX MINSTED with the electron microscope to create high-resolution correlative molecular maps?
Absolutely, yes. So that's not my cup of tea because I'm interested in exploring the physical limits, so to speak, of imaging in fluorescence microscopy. But as a say technological feat, you can imagine to combine MINFLUX or MINSTED with electron microscopy. I think it's a very powerful combination, to be honest. So for a cutting edge research lab in cell biology, I would consider that, or for a cutting edge research institution, I would do that. Yes. Why? Because with electron microscopy, of course, you get say morphology to some extent, of course, with very high spatial resolution nowadays, but you don't get specificity. So it's very hard to say, okay, this particular protein that I'm seeing now, because you don't have this specificity contrast that fluorescence microscopy can offer. And then by combining, say, electron microscopy, cryo-electron microscopy, for example, 3D cryo-electron microscopy with MINFLUX or MINSTED, you have a very, very, very powerful combination, very powerful combination. I'm sure this will come. As I said, this is not so much my cup of tea because this is more or less a technology thing and interesting for a user, not for me. I'm not a user. But I think, yes, that's definitely the future. And that's very powerful.
Okay, so here is come with another relevant question. Thank you for the very impressive talk. I think the major disadvantage of fluorescence microscope is photo bleaching. Is it possible to extend this method to other spectroscope techniques?
Mm-hmm. Yeah. Yes, definitely for the bleaching is an issue in fluorescence microscopy. There's no doubt about it. But I would like to say and emphasize in this context that because MINFLUX and also MINSTED require much fewer fluorescent photons, bleaching is not so much of a problem than for the other techniques. So this is something which I think is totally underestimated at this point. So we are going to develop dyes that emit only a few photons, say 100 photons, 200 photons, and then in the end still allow you to localize the molecule with very high precision, with a nanometer precision, because the concept of MINFLUX or MINSTED requires only few fluorescence emissions, or much fewer fluorescence emissions than, say, Palm Storm or other methods. And I think this is something that has not been developed to the end. So there is a lot of potential in finding out which fluorophores or which dye are bleaching after a while. Yeah, but that's okay because the number of photons are not needed. So that's one point. The second point is, can I extend this to something that is not fluorescence? When it comes to tracking, for sure, that I'm absolutely convinced about, because the principle of MINFLUX localization is not limited to fluorescence. That's clear. You can imagine doing something like a MINFLUX tracking or localization with something that is scattering. So if that is your question, yes. The main advantage of fluorescence imaging, if you ask me, apart from the specificity and so on, is the fact that you can easily play on and off. Okay, you very easily play on and off. So something is fluorescing or something is not fluorescing. And since this is the key for the whole super resolution field, like separating by on and off in order to make molecules or features distinguishable within the 200 nanometer zone, that is not so easy to do with something else, like with another contrast modality, like scattering Raman or coherent anti-Stokes Raman scattering or something like that. It's not so easy, or reflection for that matter. It's not so easy to modulate those contrast modalities in an on-off mode. And this is one of the reasons why fluorescence has been so working so nicely with super resolution, because you can easily turn it on and off.
Okay, thank you, Prof. We still have a lot of questions coming in now. I myself have also many questions, but unfortunately the time is up. So let's thank Prof. Stefan Hell again for the wonderful talk. Okay, and thank for the remarkable work done. Thank you.
Yeah, thank you.
Good evening, everyone. Today, we are very happy to invite Dr. Venki Ramakrishnan to give a plenary talk in our Global Young Scientists Summit. Dr. Ramakrishnan has determined the structure of and the function of the ribosome in numerous states. In particular, his lab determined the first structure of the small subunit of the ribosome, in which we can understand how the genetic code was precisely be translated. His lab also determined the high resolution structure of the entire ribosome, as well as a number of translational factors bound to the ribosome and a number of antibiotics bound to the ribosome. So for his great contribution and also this breakthrough, he was awarded the Nobel Prize in Chemistry in 2009. Of course, Dr. Ramakrishnan also received numerous other prizes and titles. This include, for example, he is a fellow of the Royal Society and a member of the United States National Academy of Science. And very, very importantly, he was also the president of the Royal Society from 2015 to 2020. And he also was knighted in Britain in 2012 for his great contributions to the field of molecular biology. Okay, today his plenary topic is using electron microscopy to study ribosome in action. Okay, Dr. Ramakrishnan, please.
Hello, I'm Venki Ramakrishnan. I'm sorry I can't be with you personally in Singapore due to the pandemic, but I hope you enjoy this online lecture nevertheless. So I'm now going to tell you about how the new revolution in electron microscopy has made possible our study of ribosomes in ways that we could never do before. So to begin with, here is the central dogma of molecular biology, which says that information is typically stored in DNA, which gets transcribed into messenger RNA, and that somehow gets translated into protein. And for that translation, you need this intermediary molecule called the tRNA, which has an anticodon that recognizes a codon on the messenger RNA and brings in the appropriate amino acid to add to the growing polypeptide chain. Now, of course, this doesn't happen by itself. Cell biologists a long time ago figured out that it happens in these blobs, which you can see on the left on the endoplasmic reticulum. And when those blobs were isolated, there were particles about 25 nanometers in diameter, and these particles were called ribosomes, and that's where the act of protein synthesis occurs. Now, ribosomes are enormously complicated, so even the bacterial ribosome has about 50 proteins and 3 large pieces of RNA. It's about 2/3 RNA by mass, and it consists of 2 subunits which join together to form the entire ribosome. And of course, ribosomes from higher organisms are even larger and even more complex. Now, the way the ribosome works is that the small subunit binds the messenger RNA, which carries a genetic code. The ribosome has slots for the tRNA molecules, and it somehow selects the first tRNA above the first codon, brings in the first amino acid, and then in the so-called amino acyl slot, a new tRNA comes in, bringing in the new amino acid, and if it happens to be the correct one, the ribosome joins the first and second amino acid, and then the ribosome moves along the mRNA. At some point, the old mRNA is ejected from the ribosome, and then a third tRNA comes in, and if it's the correct one for that codon, it's also accepted, and then a bond is formed between the second and third amino acid. So you can see it's reading the code on the mRNA, choosing only those tRNAs that match the code, and then joining together the amino acids that have been brought in by those tRNAs. So it's effectively translating the genetic code into the language of proteins. Now, of course, the ribosome doesn't quite look like that simplified cartoon. Here's a picture of the ribosome where this is a sort of low resolution image from electron microscopy, and it shows that the mRNA is actually bent. It curves around the small subunit and is buried in a cleft. The tRNAs are L-shaped, and this is the tRNA holding the growing peptide chain, which emerges out of a tunnel in the large subunit. And here is the new tRNA bringing in the new amino acid. Now, of course, if you want to really understand how the ribosome works, you need a high resolution structure so you can understand the ribosome in atomic detail, which then allows you to understand the chemistry of its interactions and thereby understand the mechanism by which it recognizes mRNA and the right codons and how the amino acids are joined together in a peptide bond. All of those things are basically chemistry happening in this very large molecule and require a high resolution structure. Now, until a few years ago, the only way that you could get a high resolution structure of such a large molecule as the ribosome was to use a technique called X-ray crystallography. Now, in X-ray crystallography, what people do is that, well, let's back up a bit and talk about how you would magnify small objects normally. So if you have a small object and you want to magnify it, you typically would use a lens, and the lens would take scattered rays from the object and recombine them into a magnified image. And then you could look at the magnified image and see details. But with atomic structures of molecules is a problem, because the distance between atoms is only about 0.1 nanometers or so, but the wavelength of light is well over 1,000 times more. It's about somewhere about 400 to 700 nanometers. And so light is the wrong kind of radiation to use to look at atomic details of molecules. And the method that people had developed over 100 years ago is this method called X-ray crystallography, where you take your molecule and make it form regular three-dimensional arrays. In other words, you make it form a crystal, and then you take that crystal and hit it with a beam of X-rays, and that beam of X-rays then is scattered, and in a computer, what you do is you take those scattered rays and recombine them and do effectively what a lens does. And when you do that, you can essentially generate a three-dimensional object, a three-dimensional image of the object in the computer, and you can interpret that in atomic terms. And precisely that was done for the ribosome. So in 2000, which is now astonishingly 22 years ago, there were structures of both the large and small subunit of the ribosome, and then an atomic structure of the entire ribosome was discovered a few years later. And one thing that the ribosome structures tell us is that the ribosomes probably emerged from an ancient world in which RNA did the bulk of the chemistry of life. That is, RNA not only carried information, but also did many of the chemical reactions of life, long before proteins evolved as catalysts and as structural molecules to evolve into life as we know it today. And these structures were also useful to look at antibiotics bound to the ribosome. Many decades ago, in the 40s and 50s, a number of antibiotics that were discovered were shown to work by blocking bacterial ribosomes, but not human ribosomes. And these structures allowed us to see exactly how antibiotics were bound to the ribosome. And that, of course, resulted in people trying to develop better antibiotics. Now, moving on to the more recent method, which is electron microscopy. Electron microscopy was first discovered by Ernst Ruska in 1933. He had to wait 53 years for his Nobel Prize, which was rather unfortunate. But in fact, that wasn't the longest wait. Actually, Peyton Rouse, who discovered the Rouse sarcoma virus, had to wait even longer for his Nobel Prize. So I suppose one thing, if you think you're in the running for a Nobel Prize, you should try and be very careful and not die. So how does single particle reconstruction work? Well, here's a movie made by Wolfgang Baumeister and his team at the Max Planck Institute in Martinsried that will give you some idea. So effectively, the way that this works is a small volume of a sample containing the particles of interest is deposited onto a grid, which is only about 2 millimeters or so in diameter. And then it's blotted away. So there's a very, very thin layer of liquid. And then this thin layer of your sample is rapidly frozen in liquid ethane and then studied under the electron microscope. And what you see when you look at it is you see these particles suspended in this liquid. It's not exactly ice, but you can think of it as glassy ice or vitreous ice, because not crystalline like ice is, but it's rapidly cooled water. And so these molecules are trapped in this vitreous ice. And when you image the molecule, you're getting projections. That is, you're getting two-dimensional projections of these molecules. And this movie shows you how you can combine all the different projections that you would see, because the particles are all trapped in different orientations. So here's what it looks. So now you have your projection of different particles. And if this is the object, then you have to relate what orientation of the object gave you a particular projection. And so you can effectively map all of the different projections onto a three-dimensional sphere, which tells you what is the particular orientation of the object that gave you that projection. And then you can then recombine those projections by a back transform to effectively recreate the object. And this is a method that was developed by many people, but initially by people like Aaron Klug and David DeRosier. And you effectively end up with a three-dimensional projection, three-dimensional image of the object. Now, using exactly this method, two postdocs, Alexia Munz and Alan Brown, and then later on a graduate student named Nirupa Desai, decided to tackle the mitochondrial ribosome. And what are these mitochondrial ribosomes? Well, mitochondria are actually organelles in our cells where a lot of energy metabolism takes place. So that is where ATP is actually synthesized. And what these organelles are very complex organelles with a double membrane, with lots and lots of enzymes in the membrane, which are part of the respiratory chain, which eventually results in ATP synthesis. Now, it turns out mitochondria actually have their own ribosomes. And the reason they need their ribosomes is mitochondria have their own genome, which encode in humans, they encode 13 protein genes. So these 13 proteins have to be made by translating the mitochondrial genome. And for that, mitochondria have their own specialized ribosomes. And when Alexei and Alan and Nirupa solved the structures, first of the yeast large subunit, and then the human large subunit, then the human mitoribosome, and finally the yeast mitoribosome, they found it was very interesting. Although these ribosomes have descended, although mitochondria are descended from bacteria, you would expect that their ribosomes look very much like bacterial ribosomes. But not only do they look very different from here's an E. coli ribosome on the right. Not only do they look very different from the bacterial ribosome, but they also look very different from each other. For example, the yeast and human mitoribosomes look very different from each other, and they're almost as different from each other as they are from the bacterial ribosome. So we could never have done this work by X-ray crystallography, simply because getting enough material and being able to crystallize the mitochondrial ribosome proved almost an impossible task. And luckily, this method for cryo-electron microscopy came along, and we were able to do it. So going back to the central dogma, you know, DNA is transcribed into mRNA, and it's this mRNA which is translated by the ribosome to make protein. Now, if you look at mRNA, it's a molecule with a 5' and 3' end. And when it was first discovered, people didn't know a lot about it. They thought that maybe the entire mRNA would contain the coding sequence, that is the sequence, the codons that specified which amino acids are to be added to the protein chain. And the ribosome would simply start at one end and go off all the way to the other end and fall off. Well, it turns out that's not how it works. Actually, one of the first things that they discovered is that there's a special codon called a stop codon. Well, actually 3 of them, UAA, UAG, and UGA, which tells the ribosome this is the end of the coding sequence and you should stop here. And then there are special factors that come into the ribosome and cleave off the newly made protein so it can go off and do its thing. Then they realized that it doesn't start at the very beginning either. There's actually a special codon, which is always a methionine codon, an AUG codon, although it's made as formal methionine in bacteria. And that's not always at the 5' end. It is in some mRNAs, in a few mRNAs called leaderless mRNAs, but most of the time it's some way inside the mRNA. So there's a region between the 5' end and the start codon, which is called the 5' untranslated region, just as this region beyond the stop codon is called the 3' untranslated region, or UTR. Now, the way that, so then it has to know how to start at that methionine codon. How does the ribosome know where to start? So in bacteria, the ribosomal RNA in the small subunit has the 3' end of that is complementary to a short stretch on the mRNA just upstream of the AUG codon. So the ribosome knows roughly where to begin by sort of this base pairing between the ribosomal RNA and the mRNA. And then there are 3 factors, initiation factor 1, 2, and 3, along with a very special tRNA called initiator tRNA. Remember, this codes for methionine, but there are also methionines inside the protein. You know, lots of proteins have methionine. And those internal methionines are coded for by a different tRNA compared to the first AUG codon, for which you have a special initiator tRNA. Now, in eukaryotes and higher organisms, the mRNA is different, and in fact, initiation is much more complex. So the first thing is that beyond the stop codon, eukaryotes add a string of adenine nucleotides to the mRNA, and this is called the poly-A tail because it's a string of A's. And not only that, but the 5' end is capped by a particular diguanine residue. So it has a very special structure at the 5' end. Both of these are, to some extent, to give stability to the mRNA, you know, so that the poly-A tail and the cap are recognized and give the mRNA some stability. But they also have many other functions, as we'll see. Now, the way initiation works in eukaryotes is instead of this, the small subunit is called a 40S instead of 30S as in bacteria. The small subunit binds several initiation factors shown here, EIF1 and 1A and EIF3. And then along with that, EIF2 binds the initiator tRNA, and along with EIF5 binds this complex. to form what is called the 43S pre-initiation complex. Now, at the same time, the mRNA is being bound by a factor called EI4F, which is actually a composite of EI4E, which actually binds that 5' cap, EI4A, which is a helicase, that is, it's an ATPase that has the ability to unwind secondary structure in mRNA, and it has a molecule called EI4G, which is a very large molecule, which is what interacts with this 43S pre-initiation complex. Now, the poly-A tail is also bound by a protein called PABP, called poly-A binding protein. So effectively, the mRNA can be circularized because this poly-A binding protein, there's evidence that it can interact with this EI4G. So this complex of mRNA with the cap binding complex, the 4F complex, can recruit this small ribosomal subunit complex called the 43S complex to the mRNA, and that complex is called the 48S complex. Now, once this complex is formed, it has to scan along until it finds the start codon. That often requires ATP hydrolysis, not always. And when it finds the AUG codon, then a number of things happen. Many of these initiation factors fall off, and a new initiation factor, EF5B, binds to this complex and recruits the large subunit. And once the large subunit is recruited, this 5B itself falls off the ribosome, and then the ribosome can go along and keep adding amino acids to the protein chain until it reaches a stop codon and dissociates, and the whole thing can start all over again. And although in eukaryotes the situation is much more complicated with almost a dozen initiation factors, there are some commonalities. So every one of the bacterial counterparts, which are designated by IF1, IF2, and IF3, have a counterpart in the eukaryotic system. So you can think that there's a common core that's conserved between bacteria and eukaryotes. Now, there was and there still is, a kind of debate going on in the field about exactly how the small subunit is recruited to the mRNA, and then how scanning takes place. So there are a couple of models. In one model, the EI4F binds to the 5' end, and it recruits the small subunit downstream of it. And this would require that the mRNA is basically slotted in to that cleft in the small subunit. And then it scans along until it finds the AUG. But this means that if the AUG is too close, for example, if it's closer than this where the tRNA would bind, and let's say it's over here, it would never be found, because this is an inaccessible region, because once it binds, it can't scan backwards because of the presence of this cap binding complex. Of course, without it, it might be able to move backwards, and there's evidence from other labs like Jody Puglisi which suggests that there might be something like that going on. The other model is called the threading model, where EI4F binds here to what's called the entry site, and then somehow the cap binding protein factor EI4E dissociates, and then this mRNA can then thread into the 40S subunit. So we decided to see what a structure would tell us, and this is all using the human system with purified factors, and it's a collaboration with Chris Fraser and Masa Sokabe at the University of California, Davis. And the people in my lab who carried out this work were led by Jay Querido, a very talented postdoc, and Sebastian Kratz, another very talented postdoc who is now doing a postdoc in computational biology in Switzerland, and Yulia Gordienko, who's a senior associate, a long-time senior associate in the lab, and Mark Scale, who did some of the mass spec experiments, which I'm not really going to talk about today. So based on the factors that Chris and Masa had purified and shown how you could assemble in vitro an initiation complex, what the lab did was to do an initiation complex and assemble it and then study it by electron microscopy. And they chose an mRNA which didn't have a start site so that they could try and capture something that might be a scanning intermediate. Because once it reaches the start site, then these factors start to fall off. So what they found was something that looked like this. And you can see, this is the small subunit in gray, and you can see all of the very large factors that completely surround the small subunit. And you can see here are two different views of the factors of the initiation complex. So what have we learned from that? Well, the first thing is that what we've learned is that the initiation, the cap binding complex of 4E, 4A, and 4G is actually at the 5' end, and the 48S binds downstream of the cap binding complex. And what this suggests is that the mRNA was recruited by slotting the mRNA into the cleft and not by threading. So it's not like the cap binding complex is binding here at the entry site and then somehow the mRNA is being threaded. Rather, it's binding at the 5' end and recruiting the 40S downstream of it. Now, when it binds, it must somehow pull the mRNA through it. And there's some debate about whether the cap is released or whether the 4E actually hangs on to the cap, in which case if the mRNA is pulled through, it must sort of loop out like this so that it's still bound to the cap binding complex. So at least the work we've done so far very strongly supports the idea that the cap binding complex actually recruits the 43S complex and the mRNA is slotted into the 43S complex, and some sort of pulling mechanism then pulls the mRNA through it. Now, if you now look at the entry site, in this structure, the entry site was completely empty. There didn't seem to be any factor bound at the empty site. But Jay Querido has now done a structure as part of the same collaboration with an mRNA that has quite a bit of secondary structure, and he's used a trick to lock 4A, which is an ATPase, so that it won't fall off and it'll be locked in place. And when he does that, he not only sees the 4F, which also includes a 4A, which is the helicase, at the exit site near the 5' end, but he sees a second 4A bound near the entry site of the mRNA. So this suggests that you might have a second 4A, and you might need a second 4A in many cases. For example, if you have highly if you have an mRNA with a lot of secondary structure that has to be unwound, then you might need a second 4A ahead of the 43S to unwind the mRNA as it scans. And so here's a model for how scanning might work. And that is, you have your cap binding complex with one of the 4As at the exit site. It has a certain role. And then you also have a second 4A, or it could be some other helicase. For example, there are helicases like DHX29, which may also serve that function. And that binds near the entry site and may be used, for example, to melt or unwind secondary structure in the mRNA in order to reach the start codon. So I just want to summarize by saying that cryo-EM has made possible the determination of structures that were never before possible because of the amounts of material you could get, or because they were unstable and so on. The reason it's so powerful is that you need very small amounts. You need a thousand-fold or less material compared to a typical crystallographic project. And the samples don't need to be, this should be homogeneous. They don't need to be homogeneous. They can be heterogeneous. And you can capture transient or dynamic complexes. And if you use tomography using cryo-electron microscopy, this is a technique which allows you to look at entire cells or sometimes slices of cells. So you can look at complexes as they exist in situ, inside cells. So all of these revolutionary advances means that we're really in a new era for structural biology where amazingly difficult projects can be tackled and important new discoveries can be made. Thank you very much.
Okay, Dr. Venki Ramakrishnan, thank you so much for a very, very wonderful talk. Yeah, it is crystal clear. Yeah, I always enjoy your your talk, your presentation. Yeah, so maybe we will have questions from the audience, but let me begin first. So as for the mitochondrial ribosome, and also you compare the mitochondrial ribosome with the like a loma, like a bacterial ribosome, etc. Then you found the mitochondrial ribosome more like a diverse. So you also mentioned like you early discovery, like a number of antibiotics bound to the bacterial ribosome, and then this can rationalize how the molecular mechanism of the antibiotics, and also is very, very useful for the new drug discovery. So my question is that, do you think the mitochondrial ribosome would be a good target for like a drug discovery to tackle the new like some antibiotics resistance crisis?
I think because we all have mitochondria, if you target mitochondrial ribosomes, it will be toxic to us. And in fact, it's believed that one of the reasons that many ribosomal antibiotics are toxic, for example, chloramphenicol or some of the streptomycin and so on, have side effects, is because they bind to our mitochondrial ribosomes, because they're closer to bacterial ribosomes, at least the antibiotic binding site. So there is an idea, though, that you can target mitochondria for cancer therapy because, cancer cells use a lot of energy. And since mitochondria are the source of, energy in the cell, if you target mitochondria, it might preferentially affect cancer cells. But it hasn't really, I don't think it has worked so well. Okay. So I think the more important thing is it will allow you to design antibiotics that bind to bacteria, but do not bind to mitochondrial ribosomes. And that way it'll be more specific and have fewer side effects.
Okay, I see. Thank you. Okay, so let me check from the question from the audience. Okay, so we have a number of questions from the audience. So like one from John Benita. Her question is there a typical 5' UTR consensus sequence like needed for proper initiation slotting, or is it a generic non-specific interaction with the ribosome, or no need?
Yeah, I think there are two things here. One is the initial recruitment of the mRNA, and the second is efficient initiation at the AUG. So I believe that for the initial recruitment, it's relatively non-specific. It's for any single-stranded mRNA. Of course, it has to be in the proper context with, cap binding complex, etc. But when you get to near the start codon, I think that's where the Kozak sequence will make it more efficient. And same with Shine-Dargano in the case of bacteria.
Okay, thank you. So we have another question from Shu Bao Zhao. Fantastic talk. So the question is, how do you think about the appearance of AlphaFold, where it influenced the research of structural biology, and what will be the research emphasis in the future of structural biologists?
I think AlphaFold is I think it's a very big breakthrough because it does allow you to calculate what the fold of a novel sequence might be. It is very early days, and so we do have to get some idea of where AlphaFold works and what fraction of the predictions are accurate and what fractions have problems. But I imagine that in the next few years, machine learning will really make a lot of progress towards fold prediction. But then we have to think about how proteins change conformation, how they bind ligands, how they interact with each other, and so on. And it's very hard to predict, but my guess is that machine learning will really help structural biologists a lot. I don't think an empirical experimental structural biology will ever go away because we need that to, first of all, to be sure, secondly, to see subtle features and so on. But I think it'll be a great tool. It'll be a very, very important tool in structural biology.
Okay, great. Oh, thanks for a great lecture. What do you think are the new directions in ribosome research? Maybe she mentioned, maybe example time-resolved EM, or how can it be applied in medicine?
Yeah, I think there are a number of questions. I think a lot of the focus in the last 20 years has been on understanding the basic structure and some of the basic mechanisms in what you would call canonical translation. And I think the future will be more directed towards control of translation. How does the cell regulate translation? Because that's a very, very important aspect of gene expression and biology. Another thing is about non-canonical translation. For example, viruses can avoid many of the normal steps during initiation of translation, and they have their own mechanisms. How do RNA modifications affect initiation and translation? So there are a lot of questions which have to do with regulation and altering the normal course of translation and quality control and so on.
Okay, thank you for the clear answer. Okay, then the one question is, thank you for the excellent talk. I have one question about the evolution of translation. Are there any transitional steps in evolution between bacterial initiation and the eukaryotic scanning model?
Yes, that's a very interesting question. Clearly, the core is conserved because the three initiation factors in bacteria have counterparts in the eukaryotic initiation factors. So there is some common conserved core to this complicated process. I don't know if we have real intermediates. I suppose one could study archaea, which eukaryotes have sort of evolved from archaea. So one could study archaea and initiation of translation in archaea. And perhaps that's a somewhat understudied field, and maybe that's something that deserves more attention.
Thank you for a great talk. Even though cryo-EM is powerful, what are big limitations of this technique?
That's very interesting. So one of the limitations, of course, is as you get down to lower molecular weight, say below 40 kilodaltons or 50 kilodaltons, it becomes progressively harder or impossible to get enough signal to align the particles and obtain a structure. So that's something that people are working on, is how to improve the signal to noise in cryo-EM. Another problem is that often the core of the molecule will be very stable and well determined, but in the periphery where you are binding, factors and so on, there's a lot of dynamics. Those periphery are not fixed relative to the core, and so as you go out from the core, the resolution becomes worse. And so that is another real problem with cryo-EM. And finally, some complexes are highly dynamic. They have an entire ensemble of structures, making it hard to, determine any one of them to high resolution. I think, though, experimentally, these problems are being tackled both by improving the actual microscopy, by better sample preparation and grid preparation, and also by software, by improved algorithms. So cryo-EM is not a static field. It's still early days. It's a bit like crystallography was in the 1970s, and people are making dramatic improvements all the time. And of course, as we discussed before, there are entirely computational techniques like AlphaFold, which will only help cryo-EM. If you have a map that's not quite interpretable, but then you have an AlphaFold model, and you can constrain AlphaFold with the model, that'll actually be more powerful. So I sense that there are going to be big improvements in structural biology.
Okay. Yeah, thank you. So there are many questions from our audience. Yeah, because I think you gave a very wonderful talk, very clear talk, so they understand, and then they have more questions. But there's a time limit, so unfortunately we cannot continue our Q&A session. So once again, with a big thanks to Dr. Venki Ramakrishnan. Thank you very much for a wonderful talk. Okay, see you.
Thank
Hopefully
you. I'm
one
sorry.
day come to visit Singapore.
Yes, I'm sorry I couldn't come this year. And let's hope that in future years things are better and I can visit Singapore again. Thank you.
Yeah. Warmly welcome. Okay, thank you.
Good evening, everyone. It gives me immense pleasure and honor to introduce today's esteemed plenary speaker and latest chemistry Nobel laureate, Professor Benjamin List from Max Planck Institute. Professor Lisp is born in Germany and did his education in Berlin and obtained his PhD in Frankfurt before moving to the States for his postdoctoral training at the Scripps Research Institute with Professor Carlos Barbas III and the late Professor Richard Lerner. He then stayed on as assistant professor in Scripps for 4 years before moving back to Germany, where he joined Max Planck Institute as a group leader in 2003. Since 2005, he became the director of homogeneous catalysis department at the Max Planck Institute for co-research, a position that he holds currently still. Professor Li's research focus is in the development of a branch of catalysis based not on enzyme or metals, but on small organic molecules termed asymmetric organocatalysis as an approach to construct more efficiently and sustainably anything from new pharmaceuticals to molecules that can capture light in solar cells. For his achievement and pioneering efforts to develop this field of catalysis, he was awarded the 2021 Nobel Prize in Chemistry, which he shared with Professor David Macmillan, who also arrived at this method independently. Excitingly, Professor Lee has recently developed a new class of highly reactive organocatalysts called strong and confined acids, which are being used in unprecedented transformations and helping to solve some of the relevant problems in chemical catalysis and synthesis. I'm sure he will share with us more shortly. Professor Lee also received numerous awards for his research achievements, and most recently, he has been named the latest 2022 recipients for the Herbert C. Brown Award for Creative Research in Synthetic Methods. Without further ado, let us welcome Professor Lis for his lecture on chemical catalysis as enabling science and technology for mankind. Professor Lis, please.
Yeah, thank you so much for this super kind introduction. It's my true pleasure to be with you today. I would rather be in Singapore, actually. It's a German wintertime, and I almost slipped on my way to the institute because the streets are so icy. And I really enjoy being in Singapore every time I'm there, and I look forward to coming again, hopefully next year. In any case, I would like to use this opportunity today to speak about catalysis because it's, for me at least, it's the most interesting science one can pursue. And I like to talk about catalysis in a broader context, not only as a science, but also to share with you a little bit catalysis as a technology, because I think it is, as a technology, somewhat underappreciated. People are well aware of, you know, the internet and farming and things like this, but they're not aware of the true relevance of catalysis, and that's my message for you today. And I would like to start out with the single most favorite reaction for me, and that is photosynthesis, actually. You might be surprised, but photosynthesis for me is really the most beautiful chemical reaction in the universe, because in photosynthesis, enzymes, biological catalysts, convert very unreactive chemicals, CO2 and water, in the presence of light to form carbohydrates. I have abbreviated them CH2O, and this is kind of how the name also suggests their structure, and oxygen. So photosynthesis delivers the stuff we need to eat and the air we need to breathe. That's why I think it's the most important chemical reaction in the universe. And in fact, oxygen, the only source of oxygen on the planet is photosynthesis. And it happens in the leaves of plants, as shown here. The moss, actually, the chloroplasts, you see these little green balls here. In these balls, carbohydrates and oxygen is generated. And glucose is just one example of such a carbohydrate, a hexamer, so to say, of CH2O. And so this chemistry is only enabled through the magic of catalysts. And that is why catalysis is, for me at least, a really fascinating science. And I came up with this idea, and I'm still fascinated with this, that catalysis, and that's why this is kind of magic for me, is just a single molecule away from a magical transformation, in which you, for example, convert two compounds A and B to a third compound C, and with magic you would just use a magical stick or say a few words. But with catalysis, one molecule in principle would be enough to do this process, and it functions because the catalyst does not appear on either side of the reaction equation. It is actually not being consumed in the process, and that's what realized this magic actually. And the catalyst facilitates this chemical process by lowering the activation energy and providing an alternative pathway to the product which requires less activation energy. So this is basically, in a nutshell, what fascinates me about the science of catalysis. But the beauty of this area is that it is not only a science, I've mentioned this before, but it also is a technology, and it has been a key technology for sustaining our life on this planet during the last 100 years or so. And I like to say catalysis feeds, heals, warms, transports us actually. But catalysis, without doubt, will also play a huge role in the future for our life on this planet. And for example, in mitigating climate change, the global warming, of course, is a problem. And I would be not surprised if also in the future, catalysis will really play a very important role in addressing these challenges. And just to show you a little bit about the history of catalysis, why I think it is a somewhat underappreciated technology, I'd like to show you 3 examples of very, very important fundamental chemical catalytic processes that have enabled our human life on this planet. Haber-Bosch, of course, is the #1 important reaction. It's kind of the human equivalent of photosynthesis in a way, probably the most important chemical catalytic process we currently pursue on Earth. And it was discovered by Fritz Haber and Carl Bosch. Both received the Nobel Prize in different years. And it involves the conversion of nitrogen and hydrogen gas in the presence of an iron catalyst to ammonia. And this process is so incredibly important because ammonia is then converted in a second catalytic process, the so-called Ostwald process, in the presence of yet another catalyst combination with platinum and rhodium to HNO3. And from HNO3, of course, nitrates are made. And nitrates, in fact, are key fertilizers. And that's why this reaction has also been called bread from air, because you need the fertilizer, of course, to grow the plants on the earth. And the plants, we are not only eating those plants, but they also serve as food for our animals. And that's why actually the growth in ammonia production over the years, this is actually showing the ammonia production from 1946 until 2007, nicely correlates with the growth of the world population. I find this pretty amazing. I found these graphics, coincidentally, it's kind of the same time span from the 40s until the early 2000s, and you see how the world population grew from, like 1 billion to where we are today, 7 billion, and this literally correlates almost 1-to-1 with the ammonia production. So in fact, in our bodies, we have a large portion of all the nitrogen atoms in our body come from this chemical process. So in a way, you could say humans are partially synthetic, which I find kind of fascinating, if you didn't know this already. The second chemical reaction I wanted to share with you today, the second catalytic chemical reaction, is cracking. And this is something I also learned actually relatively late in my career. Cracking is probably one of the most important and large-scale processes on Earth. And in catalytic cracking, what happens is you take these long-chain alkane compounds that are distilled off from crude oil, and those can then, in the presence of a zeolite, very strong mineral material, aluminum silicate, at very high temperature, be cleaved. So this is basically a carbon-carbon bond cleaving transformation in which an alkene and an alkane is formed. And this is, of course, the synthetic method how to make fuel material, gasoline, right? And of course, I mean, it's not maybe a chemical reaction of the future, but for many, many years, this has enabled, of course, our driving our cars and flying our planes and so on. And it is still one of the most important chemical reactions conducted on the planet. In fact, larger than 1.5 million cubic meters of this feedstock material is converted literally every day, amounting to almost close to 1 billion ton or so of material that is converted every year. One of the, as I said, most important chemical reaction on the planet. And the last one of this type I wanted to share with you is the Ziegler-Natta polymerization of either ethylene or propylene. And I like to show this, of course, because it was discovered by Karl Ziegler. He was the director at the institute where I am here right now, the Max Planck Institute for Kohlenforschung, coal research. And Ziegler discovered this propylene polymerization and ethylene polymerization back in 1953 and received a Nobel Prize in 1963. And as you can see, many, many materials, important materials, can be made from this. And this, people have said this discovery marked the beginning of the plastic age. Now, if you think about it, you can kind of summarize the science of catalysis with the Nobel Prizes that were given to this area, starting actually with the first Nobel Prize to a catalysis researcher that was Oswald, actually in 1909. And Oswald was kind of laying the foundations for the science of catalysis, the physical, chemical aspects of catalysis. Oswald was a real pioneer, and he understood, for example, that enzymes, biological catalysts, are by no means different to the chemical catalysts. And another aspect of Oswald is actually that in 1905, in a book review, actually, he already predicted that maybe one day chemists will be able to design organic catalysts, and he really called them organic catalysts, to catalyze chemical reactions like enzymes, but with higher thermic stability. So he was really a visionary, I would say. But the surprising thing then was that, and this is reflected with the many Nobel Prize winners that were honored for their work on catalysis in the subsequent years. There were in fact 17 prize winners. Almost all of them actually used transition metals as catalysts. And this started out with Sabatier, of course, finely dispersed transition metal catalyzed hydrogenation reactions. Haber and Bosch, I already mentioned. Bergius hydrogenated coal actually to make alkanes. And these are all heterogeneous transition metal catalyzed processes. And then until Ziegler and Natta in 1963 utilized homogeneous catalysts and again transition metal catalysts, actually, this marked the beginning of the area of homogeneous transition metal catalysis. And there were a few other Nobel Prizes given to this general area, Knowles, Sharpless, and Noyori, of course, for their work on asymmetric catalysis with chiral transition metal complexes. Chauvin, Schrock, and Grubbs for olefin metathesis using homogeneous transition metal catalysts. And then, of course, Heck, Negishi, and Suzuki for palladium catalyzed cross-coupling reactions, again utilizing homogeneous transition metal complexes. So you can basically see that until this recent Nobel Prize 3 years ago to Francis Arnold, utilizing enzymes, directed evolution of enzymes, the entire century was focused on transition metal catalysis. And I like to say, therefore, that you can call this century basically a century of transition metal catalysis. And so this may now bring you to the understanding why chemists somehow thought in the late 90s, when I was a graduate student, that catalysis basically is synonymous with transition metals. And in fact, the chemist's view on asymmetric catalysis, where we try to make mirror image molecules selectively, in the late 1990s was beautifully defined by Casey Nicolau and Eric Sorensen in a wonderful textbook, one of my favorite textbooks in chemical synthesis, Classics in Total Synthesis, where they basically say that in a catalytic asymmetric reaction, you can either use an enzyme, as Oswald already knew, or you can use synthetic soluble transition metal complexes, period. And in a nutshell, this was really how chemists viewed asymmetric catalysis. And with this sort of mindset, I decided I wanted to work with biocatalysis for my postdoctoral studies. And so I moved to the Scripps Research Institute, and I was fortunate to work with Richard Werner there, a pioneer in catalytic antibodies. And he, together with Carlos Barbas, they have just developed an aldolase catalytic antibody, a protein catalyst that, like an enzyme, like a class 1 aldolase enzyme, would catalyze an aldol reaction between ketones and aldehydes to give such aldol products, and typically with incredibly high enantioselectivity. And so my first task when I came there as a postdoc was to try to understand the mechanism of how this, I call it enzyme, actually works. And we had a crystal structure obtained of this antibody. And what I realized upon close inspection of the active site of this antibody was that there was an amino group provided by a lysine residue, and also a tyrosine residue, a phenyl group of the tyrosine residue, where this hydroxy group was hydrated. And that, I speculated, would function as an acid co-catalyst. So it's kind of a bifunctional catalysis mechanism in which an acid and an amine enable the conversion of a ketone first into an iminium ion and then into an enamine. And then this enamine, assisted by this co-catalyst, the Brunstad acid, would then react in a carbon-carbon bond formation with the aldehyde. While this aldehyde is being protonated in this transition state, you generate the iminium of an aldehyde, which is of an aldol, which is then hydrolyzed such that you end up giving the aldol product. So that was the mechanism. And when I got the chance then to build my own laboratory starting in January 1999, I thought, wouldn't it be fascinating if with this understanding, we were able to design small organic molecules that, like enzymes, would catalyze the same transformation. And you know, from my mechanistic understanding, I reasoned that all that would be needed for this catalysis by the small organic molecule would be an amino group and an acid co-catalyst. So basically an amino acid. And that, of course, rang a bell. There was already an amino acid in catalysis. In the 70s, proline, it was discovered in industry that it would catalyze certain intramolecular aldol reactions. They never were used on a technical scale. And also, somehow, the mechanism was, I would say, misunderstood. So people did not really understand how it worked. And for me then, this was kind of the eureka moment already. I realized this is probably how proline catalyzes aldol reactions. It's like an aldolase, right? It has an amino group, pyrrolidine nitrogen, and it has a carboxylic acid that could function as a Brunstad acid. And with this machinery, it could now convert, for example, acetone into an iminium ion and then into an enamine intermediate. And this enamine would then react with an aldehyde, very much like the aldolase, with the protonation of the oxy anion in the transition state to give the iminium ion of an aldol. And then the water molecule originally generated in this first step would then come in and hydrolyze this iminium ion such that you get an aldol product. And when I did this experiment, I was shocked and delighted to find that indeed proline would catalyze this reaction with remarkably high enantioselectivity. In fact, those enantioselectivity that we have obtained in this transformation were pretty much defining the state of the art. And at the time, this direct asymmetric aldol reaction was a big challenge for asymmetric catalysis. And there was only one transition metal complex available that could do this, of course, in addition to these enzymes that people have used before. So that was the initial discovery, which has now been recognized with the big prize last month. But in fact, it was not just this reaction. What really, I think, made the difference was this mechanistic understanding, sort of this mechanism-guided reaction design. And this has then led to sort of this concept, this more general concept or general generic activation mode of enamine catalysis. Basically the idea that such an amine catalyst would convert a carbonyl compound, a ketone or an aldehyde into an enamine. And then with the assistance of my great colleague Ken Haug, we came up with also a transition state model that would describe the reactivity of proline in such enamine catalytic processes. The enamine would be able to react with different electrophiles other than aldehydes and ketones. So, and in subsequent years, these are just a few arbitrarily chosen examples from my group. We could show proline catalyzes various additional enantioselective, highly enantioselective aldol reactions, not only intermolecular aldol reactions of ketones with aldehydes, but also intramolecular aldol reactions, enol exoaldolizations of dialdehydes with incredibly high enantioselectivity, transannular aldol reactions. But in addition to aldol reactions, also, for example, alpha alkylation reactions. That was really a very challenging process. Catalytic asymmetric alpha alkylations, Mannich reactions of different types were possible with high enantioselectivity, with aldehydes and ketones as nucleophiles, and even with acetaldehyde as a nucleophile. This was one of our breakthrough papers in Nature. But also alpha CX bond formations are possible, for example, with aldehydes, and hydrazidylation becomes possible with high enantioselectivity. And again, the field then started to become a field. Many, many groups, actually several also in Singapore, started joining this area and contributed massively. Beautiful transformations. So this is just a small collection. And I was also happy to see that interest in industry rose a lot. One example that I'm particularly proud of is the use of our intermolecular proline catalyzed aldol reaction. In fact, a modification of the Macmillan group in which two different aldehydes, aldolase, has been used by DSM in the Netherlands to make this aldol product, which is then straightforwardly converted into an antiviral reagent, an antiviral agent, darunavir. And the younger generation may not know this, but HIV was probably the worst pandemic of all times for humans. Several million people died in the 80s and 90s. And this pandemic could only be controlled not with the help of vaccines, unfortunately. The vaccines until today fail with HIV. So we're very fortunate with the coronavirus that we have good vaccines right now. But in this case, only small molecules help the patients nowadays. And currently, HIV patients take 3 or 4 small molecule drugs designed, as I like to say, and synthesized by chemists. And I'm happy, of course, that organocatalysis came to help in making this particular one. So over the years, of course, many, many other generic activation modes and thousands of different chemical reactions literally came out of organocatalysis. And over the years, my laboratory, we have focused on one aspect of organocatalysis that we think is very, very exciting, and that is acid catalysis. Basically, one of the 2 elements of proline catalysis, which is also, as I said, a Brunson acid. And we are so fascinated with acid catalysis because if you think about it, what acids need for catalysis is the existence of electron density. So that's the bare minimal requirement. But the beauty is that chemistry is all about electron density. And 99.999% of all chemical reactions and chemistry involves electron density, of course. And so there is this huge universe of catalyzable reactions that we, in principle, could catalyze with acids. And what we realized over the years is that when you have stronger acids, and this is a pKa scale in acetonitrile, of course, when these acids get more acidic, they also become much more reactive catalysts, not only enabling much higher reactivity, which is reflected in fast reactions and high turnover numbers, but also in the ability to activate less reactive substrates, right? The more acidic the catalyst, the less basic the substrate has to be. So this was one thing that we have realized over the years, and we have now made chiral Brunstad acids that rival the acidity of so-called superacids, triflic acid and triflimate or magic acid, a very, very strong acid. But in addition, and that's now the key to this design, in addition to being very acidic, these catalysts are also highly selective. Now, how is that possible? This is possible because we have confined the active site of these catalysts. And this confinement is key in handling unbiased small substrates and in achieving high selectivity, typically in anti-selectivity. And I can show you one of the crystal structure, actually, of one of these catalysts, an imidodiphosphate, abbreviated IDP, where you can nicely see that this active site, this is where the acidity resides, is nicely confined by these bulky groups in the 3,3' position of the bienol backbone of these catalysts. And I like to say these are really magic chiral acids, and they enable a number of really fascinating transformations, I would say unprecedented transformations. And I don't have the time today to show you all of them, but I would like to nonetheless show you 4 examples of what can be accomplished with ID-pi catalysts. These are the strongest of this family of catalysts. Reaction number 1 is an aldol reaction, a Mukayama-aldol reaction, now using the acetaldehyde enol silane as the nucleophile. And the amazing thing about this transformation, of course, is not so much that you achieve high enantioselectivity and that these aldol products are very, very valuable and that they are traditionally made in a more complicated way, typically requiring 2 or 4, from 2 to 4 chemical operations. But the amazing thing of this reaction is that it is impossible to do with other catalysts, with open active site catalysts, because as you have surely noticed, both the starting material and the product are alpha unbranched aliphatic aldehydes. And of course, normally, under normal conditions, without the confinement of the catalyst, this would lead to a polymerization reaction. And in fact, when you treat this aldehyde and the enol silane of acetaldehyde with a small amount of triflimate or triflic acid, a rapid polymerization results. This is in fact a known polymerization reaction. And with the control of the confinement, we are now able to limit this reaction to a single aldolization, which we were really excited about and just published a science paper a few years ago. So these catalysts are also extremely reactive. I've mentioned this already, and they can be used on a large scale. At least for our laboratory, this is a large scale. We can use ID-pi catalysts on a multi-gram scale in Mukayama-aldol reactions of ketone acetals with ketones as the electrophiles. This was, I wouldn't say an unsolved problem, but there were only a couple of other catalysts that, of course, required much higher catalyst loading in either engineered substrates or several stoichiometric additives. And we found that with ppm loadings of our ID-pi catalysts, such products can be obtained in multi-gram quantities and also with high enantioselectivity. And we have a whole table actually of ppm loading examples in this paper that was published in Nature Chemistry also 3 years ago. But I'd like to point out to you what that really means when you can approach a catalyst loading that is below 1 part per million. And yeah, I think I should say this. For many years in the early days, people would joke about organocatalysis. You need, this organocatalysis is not really catalysis. It's maybe a substoichiometric reagent that people are using. But now the situation is very different. We have now catalysts that rival enzymes in terms of turnover numbers. For example, with this system here, we can go below 1 part per million. For example, if we were able to use 0.5 parts per billion, 0.5 ppm, 500 parts per billion, that would mean that 1 milligram of this catalyst would be able to produce 1 mole of the product, 388 grams. And on a technical level, that would imply that a kilogram of our ID-pi catalyst would be enough to make 1 megamole of the product. So this would be 388 tons of the product, which is kind of the amount a blockbuster drug is typically required at. So 1 kilogram of a catalyst would make 388 tons of a product. So that illustrates to you, I hope, the kind of sophistication that organocatalysis has reached nowadays. And last but not least, another unprecedented chemical reaction, the hydroalkoxylation of olefins. And that was another big breakthrough, I would argue, for organocatalysis. Finally, the ability that we can also activate olefins. And that was, of course, the domain of transition metal catalysis for many, many years. And finally, we can use strong and confined acids to also engage simple olefins in catalytic asymmetric hydrofunctionalization reactions. And last but not least, the last reaction I wanted to share with you in the context of the strong and confined acid catalysis is a silyl cyanation of 2-butanone. And that is actually so fascinating because the product of this reaction, this cyanohydrin, in this case it's silyl protected, is an important intermediate in the synthesis of 2 pharmaceuticals. And that has led to the situation that all different types of catalysts for this reaction, and it's interesting, this is a reaction that can be catalyzed with any type of catalyst, with a transition metal complex, with an organic catalyst, and even with enzymes. And all of those have been tried for this transformation, but none has delivered satisfying enantiomer selectivities. And even engineered enzymes only achieved enantiomer selectivity below 90%. So this is actually the first example in which an organocatalyst clearly sort of outperforms, I wouldn't say, but reaches the kind of level of selectivity with small and unbiased substrates that is normally only known with enzymes. So I would like to stop here in talking about organocatalysis, but I would also like to share with you some thoughts of the future of catalysis. Of course, we're not going to make so much more fuel and plastic in the future, but catalysis, I've promised this in the beginning, will still play an important role in the future. And I think a formidable challenge for chemists right now is to create an artificial photosynthesis. I'm not the first, of course, to telling you this, but wouldn't it be beautiful if we could take, like a tree, CO2 and water from the air, basically, or the soil, and in the presence of light and catalysts, convert this into kind of a chemist's carbohydrate. And a chemist's carbohydrate is, of course, synthesis gas. You will see that it has the same formula, CH2O, and it's a mixture of carbon monoxide and hydrogen gas. And as has been discovered, I haven't had the time today to speak about it, at this institute, this with the Fischer-Tropsch process can be converted into fuel, actually. And of course, the only other byproduct would be oxygen in this process. So it would be kind of a chemical synthesis of oxygen also. And this fuel then that is generated via Fischer-Tropsch, we could, if you really liked your Porsche or your Mercedes, you could still drive it with the combustion engine, because this would be kind of a sustainable way to make fuels, alkane fuels, and we could still continue driving cars and flying planes and so on. And but this is already being pursued. So there's a company, actually a startup company in Switzerland, that is already doing this. Not very efficient, at least not competitive with production of fuel from oil. But I think this could be a powerful technology for the future. And I'd like to finish maybe not so serious, but perhaps, who knows, maybe serious, with the essence of photosynthesis, maybe as sort of a motivation for you guys, the next generation. This could be maybe the most important chemical reaction that chemists have ever developed. So can you take CO2 and convert it in the presence of light and catalysts to oxygen and C? It's basically a deoxygenation of carbon dioxide. I would argue that this could be, if it would be realizable, the most important chemical reaction that chemists can work on. And I'd like to motivate all of you to think about this. Are there ways to accomplish such a transformation? Because with coal, of course, we can make anything. We can again make fuel if you want to. We can make materials. We can even build buildings. We can make essentially all of organic chemistry from C in the form of coal. And it would give also my institute, the Max Planck Institute für Kohlenforschung, for coal research, a new meaning if we were able to do something like this and produce oxygen, of course, in the process. And I think this would be really a lovely process. And I, as I said, want to encourage you to think about it. I mean, it might be tough and it might not be possible, but I think it would be a great process. And to make it even more challenging, how about not making coal in the process, but diamond? And with that somewhat not so serious idea, I would like to end my talk by showing you a picture from October 6th. This is my group in a really excited state. We were all, of course, massively happy. You can see the big smiles in the faces, and I would like to thank my great group for, being so enthusiastic about catalysis like me, and being brilliant minds, working hard, and being really dedicating their love and their passion for organocatalysis. I'd also like to thank funding agencies, the companies that have supported us over the years. Currently, it's BASF, but also the European Research Council, and most importantly, of course, the Max Planck Society for giving me this incredible freedom to pursue my dreams pretty much as I like to pursue them. I have great freedom in topics I work on, and I have great laboratories and a huge group, and I'm very, very grateful for this enormous trust and freedom to the Max Planck Society. And last but not least, I didn't want to miss out in sharing all the names of all the people who have worked in my group over the last 22 years. And with that, thank you very much again for having me here today, and I'll be happy to answer questions. Thank you.
Well, thank you, Professor, for giving a very inspiring talk. Now it's time for our question and answer session, right? Maybe we'll start off with a simple one, Professor
Thank you,
Lis.
Professor, for giving a very inspiring talk.
The first question will be, how easy and sustainable will you say specialized organocatalysts are to make?
How easy and sustainable? That's the question.
Yes, how easy and sustainable are your specialized organocatalysts? That you can make them. How do you make your specialized organocatalysts?
Yeah, as a organic chemist, I'm very optimistic, of course, that we can always make organic molecules. The beauty is, in the past, the last century was the century of oil and coal, and all the chemicals, all the materials, the catalysts and the dyes and the perfumes and the pharmaceuticals were ultimately generated from those fossil materials. And of course, ultimately, that is probably not sustainable. At one point, we will run out of oil and coal. And then we have to find new sources of carbon. And of course, I would say, and that's what I said in the very end of my talk, the most elegant source of carbon would be carbon dioxide, right? So let's create a new, really sustainable chemistry that starts rather than ends with CO2. So that's one of my missions. But I'm very optimistic that this can be done. In fact, it already is possible to do it this way. And ultimately, it's just a matter currently of price, like how much is crude oil versus how much would it be to make your carbon materials from CO2.
Right. Maybe following on with a related question. So to what extent do you think producing fuel using catalysts can be an alternative to electric cars?
Sorry, that I didn't understand. How could organic catalyst be an alternative to electric cars?
So to what extent do you think we can produce fuel using catalysis as an alternative to using electric cars?
Oh, okay. Sorry, I misunderstood. Yeah. No, that's a great question. I as I said, I mean, my personal preference
is an electric car, because the electric car has many, many practical advantages. And not the least is it doesn't make a large amount of noise. And it also doesn't produce toxic exhaust, right? How beautiful is that in our cities? Then, you know, Singapore would be free of exhaust, car exhaust. Our children would breathe in just pure oxygen. I think I would really like that. But having said this, I think there's still then a sustainable way in using combustion engines. For example, our planes, we cannot use electricity there. For some reason, it's technically very, very challenging, right, to fly a plane with electricity, a big plane at least. And so we could do this then with good conscience because we would produce the fuel from CO2, right, using catalysts. So yeah, I think this would free us from certain limitations if we were able to make fuel sustainably.
Right, certainly. So in your view, maybe to a slightly different type of questions, what are the benefits and challenges of combining chemical and biocatalysts for synthesis? And what concept should we keep in mind while developing such a scheme?
Yeah. So I'm open to any type of catalysis. As I said, I really love catalysis, any type, like, you know, an enzyme, even a transition metal, if it's not a very expensive or toxic metal, or if you can recycle the catalyst. Transition metals are really unique in their reactivity, so they're also great catalysts. We concentrated on organocatalysts, not so much because they are better inherently. I mean, of course, proline is beautiful because it's edible and non-toxic and so on, and certainly sustainable, but more because it was sort of an ignored field, right? So that was sort of what drove us. It's not with the message, this is a better technology. With regard to biocatalysis, I'm a great fan of this whole area. And it's really nice to see how, thanks to the work of Francis Arnold and Manfred Raetz and many other people, they can now sort of, by directed evolution, create biocatalysts that catalyze the chemical reactions we are interested in, that are may not be so much needed for life, right, in our bodies and so on, and in plants. So that's really fascinating. And I also see that people are already working on combining biocatalysts with organocatalysts. There are organocatalysts that work in water. People have done this even in a one-pot operation. You have enzymes present and you have organic catalysts present, and you have a whole cascade of reactions delivering a drug molecule, for example. And in fact, you can combine all types of catalysis, and people are working on it. I think it's very, very beautiful and very promising, and we'll get more and more into like a biomimetic situation where we have a situation that is ongoing in our cells. There are many, many different catalysts at the same time, and somehow everything is orchestrated in a beautiful and meaningful way.
Sure. Thank you, Professor. I think maybe moving on to the next questions, right? Given, you know, how enzymes can be, you know, how nature evolves, you know, enzymes towards a particular functions. Do you think it's possible to evolve synthetic catalysts, you know, in a similar way of how, you know, enzyme involves enzymes, nature involves enzymes?
Wow, I mean, there's the question I think is interested in also winning a Nobel Prize. So it's definitely, sounds like a very, very good program, but not for a program for a weekend of research, but maybe for a lifetime. It's going to be really challenging, but nonetheless, you know, a formidable challenge. Imagine we could be doing this. I would be really, really fascinated. I mean, in one way, you know, what is so nice about evolution is you have this diversity of catalysts that you can generate so quickly and so easily, right? Thousands and hundreds of thousands of different catalysts can be generated with small modifications in the DNA. But how do you have such an information-based approach to the synthesis of small molecule catalysts? I don't know that, but, you know, congratulations for thinking about such an important question. It can really, I think it can shape a research institute with a very nice program.
Thank you for your wonderful comment. So in another questions, right, is really about industrialization of your catalyst, right?
Yeah.
When do you think, you know, such a catalyst, right? Most of the processes are using transition metal catalysis to produce things. how long do you think it will take us to use, to reach an era of using, organocatalysts?
Yeah, I
Is
think
it
it's
possible
already
to replace them? Yeah.
Yeah, I think this process is already happening. What I realized, actually, Dieter Enders, just shortly before he died, told me that he has done the research, and in terms of academic research, asymmetric synthesis is nowadays dominated by organocatalysis, so publications, right? It's the number one approach to asymmetric chemical synthesis. I find this kind of remarkable. And I'm very optimistic that this will also happen in industry, little by little, of course. And it's not so much about replacing transition metal catalyzed processes, even though this is also happening. I think hydrogenation, it's probably, in terms of asymmetric small molecule catalyzed processes, the number one approach in industry right now, has disadvantages, right? You have to work with a gas that can detonate. I mean, it's nice, it's kind of clean, and everything looks smooth, but you have to work with pressurized, kind of dangerous gas. But there's also a scientific drawback of this design, I would argue, and that is, before hydrogenating something, you need to establish a pi bond, right? And the pi bond involves like a Wittig reaction or Knoevenagel condensation, but it involves some kind of additional chemical operation and often producing byproducts, right? So you have the pi bond formation and then the hydrogenation. It's a two-step sequence. And of course, all steps matter, right? And strategically, I would argue, and that's my scientific point, organocatalysis often creates sigma bonds, right? So you have the two stereogenic centers already established in the single step. So I think there's even a strategic advantage sometimes of organocatalysis. I'm very, peaceful. I don't want to exchange anything. I think all of these different approaches, transition metal catalysis, especially also biocatalysis, of course, this is heavily on the rise thanks to directed evolution, and organocatalysis will be used in the future.
Right. Maybe a specific questions regarding your recent ID pi catalyst. Right. The loading is very impressive. But one other issues about organocatalysts is poor stability under forcing conditions. Right. Do you recognize this problem in ID pi catalysts?
Well, if you think about like high temperature processes, catalytic cracking, for example, we probably couldn't use organocatalysts. At 500 degrees, they would all burn, right? Like the organic material. I mean, that's I would admit, a limitation of organocatalysis. I'm happy to admit this, but fortunately, often the types of catalysts we are using now, the ID pi catalysts, they're really at the frontier of reactivity in small molecule catalysis. They're extremely reactive, and often we have to cool down the reactions because they're so rapid and so exothermic. So I agree. Probably they might not be the best materials currently. Maybe it changes in the future. I always want to be open for more robust organocatalysts for high temperature applications. But there's plenty of low temperature applications, room temperature applications, where organocatalysts work really, really well.
Right. So thank you, Professor List. Our time is up. Maybe I'll end off with just a final question, with your parting remarks for us, regarding the creation of carbon and oxygen from CO2, assuming that it could one day be possible, right? With someone really interested to know, what do you think will be the bottleneck of this process?
So for me, this is kind of this chemical reaction, as a real chemical reaction, is unknown. And perhaps we will never be able to do it, like convert directly CO2 to CnO2 with a catalyst and light. I think it might be really, really difficult to do, because, you always have to keep in mind, you generate coal, carbon particles and oxygen. So that's a very nice mixture for creating a fire, right? So the reverse reaction is much more preferred. Right, so that is already inherently challenging. You need to separate oxygen as quickly as possible from the highly flammable carbon material, right? But I'm thinking more in terms of, like, even if you think about, for example, making plants, if you plant more trees, like billions of trees, the trees, in fact, are doing this already. They pick up CO2 and, in this case, water from the atmosphere and create carbohydrates. And if you would now use this material and just dehydrate it again, you would also generate coal, right? So in principle, this would be already kind of would be a realization of that vision, planting in an enormous amount of trees and then basically creating coal out of these trees, right? Because coal you could put back into the soil and store it there as a carbon sink for the next, I don't know, thousands of years, right? Millions of years, in fact. We know it's stable, right? So this would be one way to do this, but there are other ways like biocatalysis. They discovered bacteria that produce carbon. So somehow they make carbon, right? Isn't that fascinating? And then maybe with bioengineering and directed evolution, you can assemble bacteria that out of CO2 and water produce carbon, right? I mean, how lovely would that be?
Thank you, Professor Lis, for all your wonderful suggestions and inspiring talk. We have come to the end of our question and answer sessions. And thank you very much. And we hope to see you in Singapore very soon.
Yep. Yeah, I will look forward to. I hope I come this year or next year. Thank you very much for having me with you today, even
A very good evening to all the guests who have dialed in for this session. I'm Min Hong, a group leader at A*STAR, and I'm very honored today to introduce to you 3 young scientists who will be sharing with us their very exciting research that they're doing. First up, we have Dana Cohen of Tel Aviv University. Dana is a PhD student in the Department of Material Science and Engineering. She graduated summa cum laude from Ezra College of Engineering in Jerusalem, Israel, and has won many awards, such as the Faculty of Engineering Excellence Award for Outstanding Achievements at Tel Aviv University. Today, she will present her work titled Structural Characterization and Crystallization Kinetics of a Supramolecular System on a Microfluidic Platform.
Okay, so hi everyone. My name is Dana Cohen-Gerasi, and I will be presenting today my research about the structural characterization and crystallization kinetic of a supramolecular system in a microfluidic platform. This study was under the supervision of Professor Yossi Shacham Diamand and Professor Lee Adler-Abramovich in the Department of Material Science and Engineering in Tel Aviv University, Israel. And it was recently published in Chemistry of Materials Journal and was selected for the front cover. So I will start with a short introduction to molecular self-assembly. Molecular self-assembly begins from local interactions among molecules. When a trigger is applied, they spontaneously and independently form ordered supramolecular structures, like smart puzzle pieces. And molecular self-assembly can be in biology, chemistry, and material science. And a lot of effort has been made by scientists around the world, including our group, to exploit the naturally evolved principle of self-assembly regarding to peptide nanostructures to design tailor-made materials for various applications. So in this slide, you can see a lot of application for peptide nanostructures. For example, for energy storage devices, for sensor, drug delivery uses. And in our lab, we are specifically interested in 3D hydrogel scaffold for tissue engineering. So our lab recently published this paper regarding FMOC pentafluorophenylalanin. We incorporated the nano assemblies inside a composite material, and we enhanced the antibacterial properties of this material while maintaining its biocompatibility and mechanical properties. So this is one reason why these peptide assemblies are of great interest for us, for tissue engineering and in dentistry in particular. So what was the motivation for my study? Self-assembly is a key process in natural systems, but gaining control over the self-assembly process in a precise manner is a major challenge. Therefore, there's a great need to understand fundamentally insights into the self-assembly mechanism in order to be able to control it. So I wanted to enhance the understanding of the mechanism underlying the self-assembly of FMOC pentafluorophenylalanin. And in not so many words, I want to investigate the self-assembly process in order to be able to control it, to design tailor-made materials for my own needs, for example, for tissue engineering. So how did I do it? First of all, I used the solvent switch method to trigger the self-assembly. And then we thought that only the peptide that we choose or the amino acid that we choose affect the nanoassembly that we received. But as you can see, when I change the solvent the solvent percentage and the concentration of the peptide, I also change the nanoassembly received. So the solvent that I'm using has a major effect on the nanoassembly received. For example, in DMSO, in lower ratio, I received a fibrillary gel, and in high concentration, I received crystals. And the other way, in ethanol. So what we can know from this thing is that the solvent has a major effect on the nanostructure and assemblies that we receive. This way we can fine-tune and adjust the nanoassembly to our needs. And to look deeper inside the fibrillary gel, I took it to electron microscopy, and as you can see, in the same specific condition, only by changing the solution from ethanol to DMSO, I received different fibrils. With ethanol, I received nanofibrils that are straight, but with DMSO, I received twisted ribbons. I could also solve in high resolution, by the use of powder X-ray diffraction, the crystal structure of this amino acid. And this gives me a lot more information regarding how the self-assembly occurs and what stabilizes the crystal structures. For example, here you can see pi-pi stacking and also hydrogen bonding. I also used real-time monitoring using microfluidic device. So in my device, I have two inlets, as you can see. I have a mixing channel that can mix together the two solutions. And then I have a main channel with pillars that can interrupt structures inside them. So this is my device. And why use this approach? Because I get real-time monitoring of the self-assembly process. I can study the nucleation and growth mechanism. And also the assemblies can be imaged, monitored, and analyzed, of course. So what I figured out is this really cool movie. I can see a phase transition of 3 distinct phases, not only 2, but 3. I see spheres that are disappearing, fibrils from the right, and crystals. And you can also see it here in a magnification. C, D, and E represent the 3 different phases. So in this real-time monitoring, I could reveal for the first time the spheres that are metastable phases that are not remaining. And you can see also that because they are separated, I can quantify the area of each phase versus time. And you can see that the spheres are decreasing and the fibrils and the crystals growing on top of it. So basically we can say that this system of phase transition is thermodynamically driven. I like to think about it like a roller coaster of energy that transfer the energy from the spheres to the fibrils to the crystals. That is the most stable state. Another thing that I can do using this method is to apply kinetic modeling. Like, for example, I chose the Johnson-Mel-Avrami-Kolmogorov JMAK theory of crystallization. And I changed the temperature from 25 to 55 Celsius degree. And I applied this equation of the Avrami equation. And in this equation, I can find those kinetic parameters K and N. And to see that N is 1.5, this is its value is 1.5, meaning I have in my system heterogeneous nucleation with one-dimensional rod-like growth. And also I can apply the Arrhenius equation and use it to find the activation energy. And this activation energy is in line with the crystal structure and the different arrangement of the self-assembly. I mean, the pi-pi stacking and the hydrogen bonding are in line with this activation energy. So to conclude, I can use the self-assembly and I can control it by only changing the solvent condition and the peptide concentration, and by using high-resolution structural analysis, I can fine-tuning the exact nanostructure that I need. I can also use powder X-ray diffraction to solve these crystals and to get a much better understanding regarding the self-assembly bonding and what stabilizes the crystal structures. I also used microfluidic approach for real-time monitoring, and by this approach, I revealed this sphere phase that is metastable. And we can use the spheres, for example, to encapsulate structure and use it for drug delivery. So I can also have a way of controlling the system by this approach. And I can also apply the kinetic modeling and use it to calculate these parameters that are important for me to the understanding of this self-assembly process. So I want to thank all my supervisors and team members from the Adler Abramovich group and from the Shaham Diamant group, and my collaborators, Professor Rudi Gazit from Tel Aviv University and Professor Thomas Knowles from Cambridge University. Of course, all the founding that help us do this research. And thank you very much for listening to me. I will be happy to apply any questions that you have. As I mentioned, this research was recently published. You can scan the barcode and get right into it.
So thank you very much to Dana for that very interesting presentation. Now the floor is open for any questions, so feel free to keep the questions coming. We'll be happy to take the questions as they come in.
Okay, thank you.
So while we're waiting for the questions to come in, maybe let me just start off with the first question for Dana. So Dana, in the work that you have presented, you have presented a lot of data on a well-studied amino acid. So just wondering if you have tried this system on other model amino acids, and also what are some of the applications that your work may bring?
Okay, so thank you for the question. So yes, I applied this model and this study that I did on other molecules that I also has fluorine atoms, and we are using this to understand the self-assembly process of each amino acid or peptide, short peptide, and we are using it for as antibacterial coating or antibacterial structures that we can incorporate in antibacterial coating for dental tooth or other applications.
Thank you. just updating the system to see if there are any questions coming in. So feel free, to everyone who has dialed into this session to keep their questions coming in.
So I also would like to say thank you for inviting me, and I'm sorry that it's like this online, and I hope to meet together when the COVID will end.
Definitely. Great. So maybe we'll just give a few more seconds to see if the audience has any other questions. While we're waiting for additional questions to drop in, just wondering, Dana, given your expertise in supramolecular chemistry and microfluidics work, and also some of the applications that you have identified for us, is there some work that is in the pipeline that you want to share with the audience here as well? Both in terms of collaboration or just sharing more about the work that you're currently leading at Tel Aviv.
So basically, we're trying to develop more models and to use other microfluidic devices to investigate the mechanical properties or the self-assembly properties of other short amino acids, and to use it also to apply it as a sensors. We're trying to do conductive hydrogels also by those amino acids and molecules. And this is what we're focusing right now.
Great. Thank you so much. So I think the audience, if you have further questions, definitely reach out to Dana. I think she'll be very keen to address your questions either right now or offline. But if there are no further questions for Dana, we'll move on to the next session for this young scientist presentation. The next session we have is from Ines Weber of ETH Zurich. Ines graduated from ETH Zurich with a bachelor's and master's in material science, and is currently a PhD student in the Department of Mechanical and Process Engineering. She has published widely in the field of sensors and catalysis, and have won several awards, such as the Best Poster Award at the European Aerosol Conference. Today, we're very excited to have her share with us her work on novel gas sensors for emerging.
My name is Ines Weber. I'm from ETH Zurich, and today I would like to talk about novel gas sensors for emerging applications. In our lives, we rely heavily on our senses. In fact, we have put tremendous effort into translating those into electronic devices. Our smartphones, for example, can hear through microphones or voice recognition. They can see, identify faces, adjust brightness, or take images both in the visible or IR regime. And they can feel touch or identify our fingerprints. However, currently, they are not able to taste or smell. And this despite the fact that there is a huge potential in such chemical recognition. For example, in breath analysis, we could do disease diagnosis, or such detection could assist lifestyle monitoring. To put this into context, nowadays, the expenses for asthma treatment are $56 billion each year, and this could greatly be improved if we could monitor these parameters routinely in breath. Another example is air quality control. Urban population is exposed to air pollution, in fact, 96%. Routine pollutant monitoring is thus urgently needed to identify emission hotspots. A possibility to do chemical recognition or chemoresistive gas sensors. The advantage of those is that they are highly sensitive, they are compact and inexpensive. Unfortunately, however, they lack selectivity, and this is crucial as they are typically used in environments that are highly complex, such as breath or indoor air that contains more than 500 interference. To illustrate this, I'm showing you here a sensor and a complex matrix with many molecules. Now, this sensor is not capable of detecting only one of the molecules, such as the green one. A simple approach that we can use is to implement a filter upstream of our sensor, in this case a catalytic filter, that lets only the green target analytes pass. And today I would like to show to you with two examples how we can use this approach. First, to do breath analysis and detect acetone, and second, to do air pollution monitoring to detect benzene. Let's start with the first example. Obesity is a global health challenge. As you can see here, the average body mass index is above 25 in many countries, which is considered to be unhealthy. In fact, obesity leads to more than 4 million deaths each year. It would therefore be highly beneficial if we could monitor fat burn rates. And we can do this through the biomarker acetone that forms while we are burning fat, and because of its volatility, leaves our body through the lungs and can be detected in our breath. The advantage of this is that we can do non-invasive analysis, routine measurements, and get highly personalized feedback. How do typical chemical-resistive sensors respond to acetone? Here you can see one example, which is a silica tungsten sensor, and you can see that it nicely responds to acetone, but unfortunately also gives response to another analyte in breath, such as isoprene or ethanol. What happens now if we put a catalytic filter in front of this sensor? By using a platinum alumina catalytic filter, all the interference are effectively removed and only the acetone remains, resulting in very high selectivities greater than 250. In other words, the catalytic filter here enables superior acetone selectivity. At this point, we were curious to see how this detector would perform in real breath. And for this, we conducted a pilot study with 9 volunteers that would first do an exercise protocol on a bike and then rest for another 3 hours. You can see here exemplarily the acetone concentrations for 2 volunteers. You can see that both volunteers gave breath pulses during the first 60 minutes where they were on a bike, and then within the next 3 hours when they were resting. Most notably, we can see that our volunteer here on the left hardly changed in acetone concentrations, while the one on the right shows a steep increase, meaning that this person here burned a lot of fat and this exercise protocol was quite effective. Note that this data was measured with a high-resolution mass spectrometer that costs roughly $250,000. How does our detector perform in comparison to this? Now, luckily, our detector shows quite good agreement with a mass spectrometer, and this despite the fact that it is low cost and quite compact, as you can see here, the filter and the sensor in comparison to a €1 coin. So our low-cost detector recognizes different metabolic responses. It is also in very good agreement with a mass spectrometer, as I'm showing you here for all 9 volunteers, where you can see the sensor performance on the y-axis in comparison to the x-axis with a mass spectrometer. In conclusion, this detector could be highly promising to do personalized monitoring, for example, of exercise or dieting. Let's move on to the second example. Benzene is a global concern. In fact, accidents related to benzene have cost several hundred victims throughout the last years in India, the US, and in China. In addition, we are all exposed to benzene on a daily basis, for example, from cigarette smoke, at petrol stations, or from car exhausts. The problem with benzene is that it is carcinogenic and causes leukemia. And because of this, several organizations have set regulations into place, as you can see here. For example, in the UK, the exposure is limited to 1,000 parts per billion ppb. This is lower, for example, in the United States with 100 ppb or in the EU with 50 ppb. The strictest limit is set actually by the World Health Organization that states that there is no safe level of benzene exposure at all. Because of this, we wanted to make a device that is low cost, compact, and can detect benzene in this concentration range. So we used, again, a similar approach as before, and I'm now showing you a picture of what our detector looks like. So here you can see that, for example, indoor air would enter through the inlet and then first go through the tungsten trioxide catalyst. this catalyst here removes all the interference except for the benzene. The benzene then carries on to a palladium tin sensor that is quite sensitive and is then analyzed with a microcontroller, which in this case is a Raspberry Pi. At the end, there is a pump that provides a continuous flow from the inlet to the outlet. And I'm showing you here another picture of the pump where it is better visible against the white background. Note that this device is portable, which is highly promising if we want to use it in a widespread environment. So how does this detector perform in real indoor air? For this, we tested it in our laboratories. Now, luckily, our laboratories do not contain benzene, so we deliberately spiked the laboratory air with benzene concentrations. And you can see here again the sensor performance on the y-axis compared to the mass spectrometer. Most importantly, there is very good agreement over the entire concentration range. To challenge our detector further, we added also additional 1,000 parts per billion of xylene and toluene, which shows deliberately xylene and toluene as they are also aromatic molecules and thus similar to benzene, and typically such chemoresistive sensors fail to differentiate between molecules within the same chemical family. But here, luckily, we can see that the xylene and toluene does not seem to affect our benzene response, and we still get quite good agreement between our sensor and mass spectrometry. Finally, I'm showing you here again the guidelines starting from 50 ppb with the EU to 1,000 ppb of the UK, and you can see that our detector nicely spans the entire concentration range. To conclude, I hope to have shown you today that selective filters and highly sensitive sensors can be combined into accurate, portable, and low-cost devices. And such devices may be promising for various applications, such as breath analysis for acetone or air pollution monitoring for benzene detection. And it is my vision that in the future, such chemical sensors will be integrated into our smartphones in a similar way that today the physical sensors are already. Thank you very much for listening.
So thank you again to Ines for that very fascinating and engaging talk on gas sensors. Similarly, we would like to invite the audience to send along any questions which they might have on Ines' work, and we'll be happy to take them as they come in. So while we're waiting for the system to populate with questions, similarly, let me just start off by asking Ines a very quick question. So Ines, it's interesting that the systems that you presented appears quite selective. Can I understand the mechanism of how the catalytic filter actually work in helping to ensure this degree of selectivity?
Yes, of course. So hello first, and thank you for your interesting question. The catalytic filter works by converting the interference to non-responsive species. So technically, this means that the volatile organic compounds that enter the filter are combusted mostly to carbon dioxide. And carbon dioxide is inert and cannot be detected by the sensor. So this is the working principle of the catalytic filters. And ideally, the target analyte is not affected by the catalyst and can then still be detected by the downstream sensor.
Got it. Thanks so much. We do have a question from the audience, so let me read it out. And Ines, this is directed at you. So one of the audience members asked, how tunable are these devices for a different molecule?
This is an excellent question, thank you. So if we want to look at other volatiles, for example, we definitely need to choose another catalyst. I could see that during my research work, when we changed the catalytic filter, also the selectivity changes drastically. And here my advice is to look closely into heterogeneous catalysis that already gives a very broad database or broad materials. And there we can see what materials may be preferentially reacting with the target analytes or with the interference.
Great. We do have a couple more questions, so very fascinating. Let me read off one other question that came in. So an audience member says that it's a really nice talk, and he's asking if you can please elaborate on what kind of new and ideal materials will be promising in acting as sensors.
Yes, thank you for the question. In terms of sensing, in my research work, I found that the problem of the sensor alone is typically the selectivity and not the sensitivity, meaning that when we take even a palladium tin or a tin oxide sensor, which is the most common one in terms of metal oxide sensors, it is usually capable of detecting low concentrations, but it cannot do this selectively. So I think that emerging materials may be used also for sensors. There's a lot of examples also, such as tungsten is used or indium is used. But if they can really be very selective in a way that they are when combined with a filter, I'm not quite sure if this is possible. So I think the material choice of the sensor is important in terms of sensitivity, but not necessarily in terms of selectivity.
Great, very important distinction there. Yeah, thanks, Ines. One more question that just came in. Very interesting work. Have you also tried detection of volatile chemical warfare agents with your system, like nerve agents?
I'm sorry, I'm not sure if I completely understood the detection of which one.
Sure, let me repeat it. So this question is quite interesting. It's asking if you have tried detecting warfare agents. So for example, your nerve agents.
Oh, now I understand. I have not actually. Yes, interesting point. I have not tried that, but I think that should be possible as well. There we would have to see how it responds to the sensors. In principle, I think that should be doable. Again, we just need to look at the analytes that we're interested in, how they react with the specific materials, both the sensor and possibly a filter. But I have no experience, but it would be interesting to look into that. Thank you for the idea.
Yes, we have a very we have a great audience with very creative minds here. So one more question, which again is quite relevant when you talk about sensors. And here this question is, how long can your sensor system work before the function expires? So it's a question around the lifespan of these the platform that you have developed.
Indeed, a very important question. I have tested my filters over the time of 150 days, so several months where I did not see any degradation, and I will carry these measurements on. So far, I have not seen how they perform after a longer time, but I think that they can be quite stable, at least in a laboratory environment as we have it here. The question is then, of course, if they're extensively used and also exposed to highly concentrated or other scenarios, that may change. But the way that we operate them here in our laboratory, we have quite good stability over months.
Great to know. One final question, Ines, that just came in. What are the limitations of the catalytic filter? Are they difficult to produce?
So the limitation, I think, is not the production. Here in our lab, we use flame spray pyrolysis, but even commercial catalytic filters could work. I think one of the limitations is that it's very, very difficult to fabricate a filter that has the selectivity that we desire. So to remove all the interference, but not remove the target analyte. It's very difficult to shift this, especially if we want to distinguish between molecules within the same chemical family or with a similar chemical structure. So I think this is the most challenging task about the catalytic filters.
Thank you. So yeah, thanks again, Ines, for that very engaging presentation, and also to the audience for a very engaging discussion. So thank you, Ines, for joining us. So for the audience, the final speaker, the final speaker that we have for this evening is Maria of CNRS France. Maria is currently a PhD student in electrical engineering and is developing photovoltaic-based microgrids. She was recognized for her outstanding academic record at Comillas University and was awarded an academic excellence scholarship during her undergrad education. Further, she is part of the international working group investigating the technical challenges associated with the operation of microgrids. Today, she will share with us her fascinating work on photovoltaic-based batteryless systems to support the temporary islanding of electrical grids.
and I'm currently pursuing a PhD degree in electrical engineering at Grenoble's Electrical Engineering Lab, also known as G3 Lab. To present my research, it's important to start by explaining that traditional grids are undergoing a revolution. Here you have the scheme of a typical traditional grid. The electricity is produced by large-scale power plants that are connected through transformers to high-voltage transmission grids. These grids are composed by high-voltage lines that allow to transport the electricity through long distances while avoiding major energy losses. In turn, the transmission grids are connected to distribution grids, whose objective is to distribute the energy to the final consumers. Big consumers, such as industries, are connected to medium voltage lines, and small consumers, such as households, are connected to low voltage lines. The important thing about these grids is that they are one-way routes, because the power always flows from the transmission level to the distribution level. However, as I said before, traditional grids are undergoing a revolution, and this is because there is currently a massive integration of renewable energy plants. There are large-scale renewable energy plants that are connected directly to the transmission level, and there are also medium and small-scale plants connected to the distribution level. And the later, the small and medium plants are the ones actually causing the revolution, because they are making the power flux direction change. So in current grids, power can go from the transmission level to the distribution level, but also from the distribution level to the transmission level. On another note, there are several events that may force the opening of a distribution line, and in consequence may generate the isolation of all the grid downstream. These events can be, for example, extreme weather events or grid failures. You may think that because of the renewable energy integration, this is no longer a problem, because whenever a distribution grid is isolated, the renewable energy produced by these plants can be used to feed all the consumers placed here, which are also, these consumers are also called loads. However, this is not the case. Up until now, whenever a distribution grid is isolated, the power is cut for all the consumers here. Why is this? It's important to know that for a grid to work properly, there needs to be at least one agent making sure that the voltage amplitude and the frequency are stable. So one agent that fulfills the voltage and frequency regulation functions. In traditional grid, these agents are the large-scale power plants. And in current grids, even though there are other power plants here, they have not been conceived with these voltage and frequency regulating functions, because they have been conceived thinking that the distribution grids would always be operated connected to the transmission grid, and in turn connected in turn to large-scale power plants. So up until now, whenever a distribution grid is isolated, these renewable plants turn off, and the power is cut for all the consumers downstream. However, grid operators are increasingly interested in enabling the isolated operation of the distribution grids. I am the co-author of an international CRED report that has analyzed several European demonstrators built by grid operators that test the isolated operation of distribution grids. And in this report, it is explained that several common solutions have been developed to enable the isolated operation. One typical solution is grid reinforcement. That is, to build several parallel lines so that if one needs to be open, there are other lines that always connect the distribution grid to the transmission grid. However, this is a rather costly solution and not always cost-effective in rural areas. Another solution can be to bring emergency diesel generators that can fulfill the voltage and frequency regulating functions and that can be connected to the affected area. But these generators cause CO2 emissions, and there may be long waiting times to bring the generators to the affected area. Finally, a common solution is to install permanent batteries that can fulfill the voltage and frequency regulating functions. However, these batteries, even though they are deploying and they are being developed very rapidly, they remain very costly for the moment and they cannot be installed at large scales. What we propose in my research is to change the software of the renewable energy plants so that they can fulfill the voltage and frequency regulating function, and therefore they can feed the loads during isolated operation. This is a solution that can be regarded as a compromise, because you may tell me that it has one important disadvantage, that is time limited. So this means that the isolated operation can only last as long as the energy available from the renewable sources is enough to feed all the loads placed here. However, it has also very important advantages that make them that make the solution very attractive for operators. On one hand is that we only have to change the software of the renewable plants and not the physical assets, so it requires a minimum investment. This makes the solution very easy to expand to various areas of the grid and to deploy it at large scale. And in the end, thanks to this solution, we will learn how to control the renewable energy plants in the best possible way and to optimize the available energy. This means that in order to make the isolated operation last as long as possible, with this solution, we will learn how to use the available energy in the best possible way. There are various scientific challenges arising from the system that I propose. One of them is how to change the software of these plants to implement the voltage and frequency regulating function. But this is something that is mastered both by scientific research and in the industry. Another challenge is how to ensure that correct and secure transitions between the grid-connected operation and the isolated operation. But the demonstrators have already shown that these transitions can be correctly achieved with existing equipment in the grids. However, there is a third scientific challenge that has not been correctly addressed by the literature and that provides us a research gap. This is how to implement a power sharing strategy among the different the various power plants existing in the isolated grid. What does this mean? It means that if at each time instant all the consumers of the isolated grid will be consuming a certain amount of power, and we need to and there needs to be a strategy which decides how much power each renewable energy plant produces to feed all the loads. What we want to do is to implement a decentralized strategy. This is a strategy that does not rely at all on communication. So that does not imply building communication channels, which are costly, between the different renewable energy plants. How are we going to do this? By reinventing a very well-known power sharing strategy, which is called the group control. So, this is kind of difficult to explain without going very much into the technical details. But what we need to understand is that the frequency is a unique magnitude for each grid. So in a grid, each power plant can impose a different frequency. So solar plant 1 can impose a certain frequency, and solar plant 2 can impose another frequency. However, the dynamics of the grid will force both solar plants to reach a consensus. And in the end, in a steady state, both plants will always finish by imposing the same frequency. So, since frequency is uniform for each isolated grid, it can be used as a communication vector. Here you have a diagram representing the frequency versus the power outputted by each power plant. And the orange line represents the control law of solar plant 1. So solar plant 1, what it does is that at each time instant, it measures the power that it's outputted, that is being generated by the solar plant, and it decides which frequency it should impose. And this is the same for solar plant 2. So if there is a certain load, power demanded by the loads, which is represented by P loads, we can start with a situation in which solar plant 1 produces this power and imposes this frequency, and solar plant 2 produces this power and imposes this frequency. And to note that P1 plus P2 is equal to P loads, so to the power demanded by the loads. However, this situation is not will not last, because, as I said, the grid will force the solar plants to reach a consensus, and at the end, an equilibrium will be reached, in which the frequency is the same for the whole grid, and each power plant is producing a power which is proportional to the maximum power available for each plant. So, as I said, this is a very well-known power sharing strategy that has been applied for decades with large traditional power plants. However, if we try to adapt this strategy to renewable plants, there is a major challenge. It is that the maximum power available varies because of the ambient conditions. For example, the maximum power available in solar plants varies with the solar irradiation. That's what we are trying to develop: adaptive group control, adaptive group strategies that can resolve this issue. Another problem is that stability issues can arise in the grids if we use adaptive group controls, and this is another issue that I'm facing and that I'm trying to resolve. Stability issues is mainly the fact that there can be big oscillations of frequency of voltage and current in the grid, and that can damage the grid assets. And finally, another issue that I'm trying to resolve is that most researchers, for the moment, they use very simple models for the power plants. And what I'm trying to do is use very detailed modeling of the photovoltaic dynamics to have better quality power sharing strategies. So, some preliminary results that I have for the moment is that I have achieved 2 new adaptive group strategies, which are yet to be published, and that they achieve an optimization of the available photovoltaic power. They allow to maintain stability, and they are easy to implement. Another result of my research is that I have managed to develop a simplified photovoltaic model that takes into account the detailed dynamics of the photovoltaic cells, but it's simple to implement, and therefore it allows to simplify the whole process of designing the group strategies. Thank you very much for listening. Hope it was not very complicated. And I would like to thank the NTU and CNRS joint program that has funded this thesis, and also my thesis supervisors and all from D3 Lab, and all the collaborators from NTU and the University of Western Australia. Thank you very much.
So thank you, Maria, for that very interesting talk. So similarly, again, we invite any questions that the audience might have for Maria.
Thank you.
Thank you, Maria. So while we're waiting for questions to come in from the audience, Maria, just wanted to ask maybe a bit of a naive question, but you know, given like solar and electric vehicles, you know, being on the uptrend, and I'm assuming that these will have an impact on the grid. So I'm just wondering, you know, how does your work help in, you know, a bit of that future, right? Like the rise of electric vehicles or the increasing use of solar. Does your work have some impact on these industries or the impact on the electrical grid?
Yes. So my work is mostly related to the increasing of the solar industries. So what I propose, as I try to explain broadly with my presentation, is to use the already installed photovoltaic plants to be able to operate the certain sections of the grid in an independent way from the main grid if necessary. So what we expect, relating to your question, what we expect more and more is to have more and more installed photovoltaic plants everywhere. For example, in France, where I actually do my PhD, or in Spain, where I come from, we are currently, and for years, we have been seeing how rural areas are being being subject to a huge increase of these solar plants. And what we want to do is, what we propose to do is to use them in a more intelligent way to help the grid operators in difficult situations. So regarding the electric vehicles is kind of a separate question that we don't address in my research, but of course it will be a challenge because we expect a growth of these and a tremendous growth of these vehicles, and they will of course impose challenges of the grid because of the recharging needs of these vehicles, but they can also lead to opportunities. For example, we can think that in the future we may be able to use the batteries inside the vehicles as flexibilities for the grid. And let's imagine that in a situation when we have an emergency and we need to isolate a certain section of the grid, we can use the photovoltaic plants with my solutions during the day to operate this isolated grid during the day hours. And during night hours, maybe the vehicles that will be connected to the isolated grid can be discharged. And thanks to that, there can be some consumptions in this isolated grid, even if we haven't resolved the faults and we cannot be connected to the main grid. So yes, there are things to do.
Great, yeah, thank you. Very good insights. We do have a question from the audience. I'm just going to read it out. So audience member mentioned that it's a very interesting talk. So thank you, Maria. And the question is, he's just curious about at what circumstance the microgrids may be unplugged from the main grid. And the following question is there a safe system to manage these?
Yes, okay. So at what circumstance? There are several possible circumstances that can lead to the isolation of a part of the grid. The most common is, for example, the need. So these the scenario where my solution most applies is the case of a rural grid, where it's not profitable to build many lines. So we have one or several villages that are connected to the main grid through one line, just one line. And the problem is that whenever we need to do a maintenance in this line, these villages have to be decoupled from the main grid. And as I explained in my presentation, if you are decoupled from the main grid at this moment, even if there are photovoltaic plants there, you cannot continue the supply. So, so the situation that would lead to a decoupling would be a great failure. For example, due to a weather event and a storm, a tree falls into the line and the line needs to be disconnected, or a simple maintenance that has to do every now and then on the grid. And just to add that we are not current this solution seems more and more attractive because we are now seeing how extreme weather events are more and more often. We can think about, for example, the California fires of the last years. And there was a second, the second part of the question was if there is a system that can safely manage the transitions from grid-connected operation to isolated operation. And yes, there are. There are, as I think I explained in the presentation, is that I am part of an international working group that is analyzing several projects that have already tested this isolated operation, and they have demonstrated that with current industrial products, we can manage safely manage these transitions. The problem is that sometimes they are costly. You need to put extra sensors, extra protection devices, etc. And what my solution tries to do is, the philosophy behind my solution is what can we do with what we what is that we can do with what we have already in the grid. And that's it.
Great. Yeah. Thank you so much, Maria. And thanks to the audience for this wonderful discussion. So if there are further questions, I think offline, Maria will also certainly welcome them. But thanks again, Maria, for your time today and wonderful presentation.
It was wonderful, and thank you for the opportunity.
Great. So with that, we would like to thank the audience for having stayed with us for the whole day. And with the conclusion of this talk, we have wrapped up this session. And I would like to wish everyone here a good evening for the rest of